A photon, a single particle of light, leaves a nascent star in a galaxy that has only just begun to assemble itself from the primordial dust of a young cosmos. This particle travels for 13 billion years across an expanding void, its path bent by the gravity of invisible matter, its energy stretched by the very fabric of space, until it completes its journey in a quiet corner of our solar system, captured by a golden mirror 1 million miles from Earth. This is not a poetic abstraction. It is the physical reality of what the James Webb Space Telescope does every second of every day. It is a time machine, and the images it sends back are not just pictures, but relics, ghosts of a past so ancient that the light from these objects has journeyed longer than our planet has existed. We built this telescope to answer the foundational questions of our existence: where did we come from, and are we alone? But the answers it has begun to deliver are far stranger and more profound than we ever anticipated. The very first deep field images were not a gentle confirmation of our existing models. They were a shock to the system, a rupture in our understanding of cosmic history. Our theories, built on decades of observation and calculation, predicted that the earliest galaxies should be cosmic infants, small, chaotic, misshapen clusters of gas and stars struggling to coalesce in the turbulent aftermath of the Big Bang. We expected to see cosmic toddlers, fumbling their way toward maturity. Instead, Webb showed us young adults. It unveiled galaxies from just a few 100 million years after the beginning of time that were already shockingly structured, with well-defined spiral arms, organized central bulges, and furious rates of star formation. This was not a minor discrepancy. It was a fundamental challenge to our timeline of cosmic evolution. It was as if we had discovered evidence of Roman aqueducts in a prehistoric cave. The existence of such complexity so early in the universe's life suggests that the processes of galaxy formation are either far more rapid or began far earlier than our models allowed. The delicate dance of gravity, gas dynamics, and dark matter that we thought took billions of years to choreograph seems to have occurred in a cosmic heartbeat. This single observation has sent shockwaves through the astronomical community, forcing a re-examination of everything from the initial conditions of the universe to the very nature of the matter that governs its structure. It raises a tantalizing and deeply unsettling possibility. Perhaps the universe itself is significantly older than our current estimate of 13.8 billion years. This age is not an arbitrary number. It is a cornerstone of modern cosmology. Derived from precise measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, and the rate at which the universe is expanding, a value known as the Hubble constant. But if galaxies had time to become so mature so early, it implies that the clock may have been ticking for longer than we thought. This isn't just about adding a few billion years to the cosmic calendar. A different age for the universe would mean that the rate of expansion has been different. The density of matter and energy has evolved differently, and the entire story of our cosmic origins would need to be rewritten. We are now in a state of profound and exciting uncertainty, where the very foundations of our cosmological model are being questioned, not by a lack of data, but by the astonishing clarity of the data Webb is providing. The telescope was designed to show us the how of the universe, but it has started by forcing us to reconsider the when. This initial surprise is not an endpoint, but a beginning, a harbinger of the paradigm shifts to come as Webb continues to peer deeper into the dawn of time, revealing a universe that is not just older, but stranger and more creatively potent than we ever dared to imagine. The history of science is a history of overturned assumptions, and Webb is proving to be our most powerful tool for this necessary act of intellectual demolition and reconstruction. We are not just observing the universe, we are being forced to rethink it from its very first moments. The light from those first stars carries a message, and that message appears to be that our story is longer, and our cosmic origins more mysterious than we ever knew. The cosmic timeline is not the only grand narrative being challenged by these new dispatches from the early universe. Our own sense of place, our galactic identity, has been fundamentally altered. For decades, the Milky Way was held up as a venerable elder, one of the first great spiral galaxies to form, a cosmic benchmark against which other, younger galaxies were measured. Webb has shattered this comforting illusion. It has discovered galaxies that are not only older than our own, but were already vast and structurally complex when the universe was but a fraction of its current age. Finding a galaxy older than the Milky Way is akin to an archaeologist discovering a fully formed medieval castle buried beneath the foundations of a simple Stone Age hut. It defies the expected sequence of development and forces a radical re-evaluation of how such structures could possibly form. The standard model of galaxy formation is a hierarchical one, known as the bottom-up model. In this picture, small, dwarf-like protogalaxies form first from collapsing clouds of gas and dark matter. Over billions of years, these smaller structures merge and collide, their gravitational interactions slowly building them up into the grand spiral and elliptical galaxies we see today. It is a slow, patient, and cumulative process. But the existence of these ancient, massive galaxies, which some astronomers have nicknamed universe breakers, directly contradicts this picture. They suggest a top-down formation process might also be at play, where vast clouds of gas could collapse directly and rapidly into massive galactic disks, bypassing the slow, incremental merger phase entirely. This would require a set of physical conditions in the early universe: higher gas densities, different temperature gradients, perhaps a different behavior of dark matter that our current models do not fully account for. The implications are staggering. If massive galaxies can form this quickly, it means that the conditions for star formation, planet formation, and even the chemical enrichment necessary for life could have been in place much earlier in cosmic history than we thought possible. We are not just observing galaxies, we are watching the universe's creative potential unfold at a speed that borders on the miraculous. The challenge now for astrophysicists is to build new simulations, new theoretical frameworks that can accommodate this accelerated timeline. It may be that the interplay between the first supermassive black holes and their host galaxies played a much more significant role, acting as gravitational anchors and engines of star formation that jump-started the process. Or perhaps the very nature of dark matter, the invisible 85% of the universe's mass, is different from what we assume. Maybe it interacts with itself or with normal matter in ways that promote faster collapse and structure formation. Whatever the answer, the discovery of these cosmic elders has demoted our own Milky Way from a primordial founder to just one of many, perhaps even a relative latecomer to the galactic stage. It is a lesson in cosmic humility, a reminder that the universe is not required to conform to our expectations or our timelines. The light from these ancient galaxies tells a story of a universe that was in a hurry, a cosmos that was building grand structures and complex systems, while our own corner of space was still a formless cloud of gas and dust. We are the descendants of a universe that was far more dynamic and efficient in its youth than we ever gave it credit for. The redrawing of the cosmic map extends beyond the chronology of galaxies and into the very architecture of space-time itself, in what was once considered the great empty voids of the universe. Webb has uncovered a structure so colossal, so utterly gargantuan, that it challenges the most fundamental assumption of modern cosmology, the cosmological principle. This principle posits that, on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and from all locations. It is the bedrock upon which the entire standard model of cosmology is built. But Webb has found a wall, not a literal wall, but a vast interconnected filament of galaxies, gas, and dark matter stretching for billions of light years, a cosmic superhighway that dwarfs any previously known structure. This cosmic wall is not just a statistical anomaly, it is a feature so large that it should not have had time to form in the 13.8 billion years since the Big Bang, even with our most generous models of gravitational collapse. Its existence suggests that the universe may not be as uniform as we believed. It may have a grain, a texture, a large-scale architecture that hints at organizing principles we have yet to discover. The formation of such a structure might be tied to the initial quantum fluctuations that seeded the universe during the period of cosmic inflation. Perhaps some of these initial ripples were not random, but were correlated over vast distances, creating a preferred axis or plane along which matter would later coalesce. This would be a profound discovery, as it would mean that the randomness of the quantum vacuum from which our universe emerged was not entirely random after all, but contained a blueprint for the cosmic web we see today. Alternatively, the cosmic wall could be evidence of a more exotic physics. Some theories propose the existence of cosmic strings, one-dimensional topological defects left over from the phase transitions of the early universe. These strings, incredibly dense and stretching across the cosmos, could act as gravitational seeds, their immense gravity pulling in matter to form these vast, linear structures. While purely theoretical, the discovery of a structure like the cosmic wall lends a new urgency to the search for such phenomena. NASA and other international agencies are now dedicating observational resources to map the extent and composition of this wall, to understand if it is a singular feature or part of an even larger, unseen pattern. If the universe is indeed structured in this way, with vast walls and interconnected filaments separated by immense voids, then our understanding of gravity, dark matter, and dark energy may need to be fundamentally revised. Gravity, as described by Einstein, works the same everywhere. But what if, on these unimaginable scales, its behavior changes? Or what if the properties of dark matter are not uniform, but vary depending on the density of the environment? The cosmic wall is more than just a large collection of galaxies. It is a direct challenge to our most cherished principles, a silent, monumental testament to the possibility that the universe is governed by rules that are far more complex, and perhaps far more elegant, than our current theories can accommodate. It forces us to confront the possibility that our view of a smooth, uniform cosmos is an illusion born of our limited perspective, and that the true reality is a far grander, more structured, and more mysterious tapestry than we ever imagined. In the midst of this cosmic remapping, amidst the discovery of ancient galaxies and impossibly large structures, Webb has also detected a whisper, a signal from the deep dark that is as enigmatic as it is tantalizing, from a distant, unidentified source. The telescope has recorded a series of mysterious light signals, pulses that are unlike any known astronomical phenomenon. These signals are not the chaotic bursts of a supernova or the regular lighthouse-like spin of a pulsar. They exhibit a complex, repeating pattern, a structured sequence that seems to defy a natural explanation. The scientific community is, rightly, exercising extreme caution. The history of astronomy is littered with signals that were initially thought to be of intelligent origin, only to be later explained by a newly discovered natural phenomenon. The first pulsars were playfully nicknamed LGM-1 for little green men before their nature as rapidly spinning neutron stars was understood. And so, the leading hypotheses for these new signals remain grounded in known, if extreme, physics. Could they be originating from a new type of celestial object, perhaps a magnetar with a complex magnetic field that modulates its emissions in a periodic way? Or could they be the result of a binary system of two compact objects, like neutron stars or black holes, whose orbital dance creates a complex pattern of gravitational lensing, causing the light from a background source to flicker in a structured way? These are all plausible, if unproven, explanations. NASA has put observatories around the world on alert, hoping to capture the signal across different wavelengths of the electromagnetic spectrum, from radio waves to gamma rays, to triangulate its position and analyze its properties in more detail. This multi-messenger approach is crucial to solving the mystery. A natural source would likely have a broad spectrum of emissions, while an artificial signal might be narrowly focused on a specific frequency, a telltale sign of an efficient, engineered beacon. But while the scientific process moves forward with its necessary rigor, the philosophical implications of the signal are impossible to ignore. The very possibility, however remote, that these signals are a product of intelligence is a thought that changes everything. It would be the single greatest discovery in human history, a definitive end to our cosmic solitude. It would force a reevaluation of our place in the universe, our purpose, and our future. For this reason, the search for an explanation is being pursued with an intensity and a global collaboration rarely seen in science. The signal is a puzzle, wrapped in a mystery, inside an enigma, but it is a puzzle that humanity is now united in trying to solve. Whether its origin is a new wonder of astrophysics or the first greeting from a distant intelligence, the outcome will be revolutionary. If it is natural, it will reveal a new process in the universe, a new way in which matter and energy can interact. If it is artificial, it will reveal that we are not alone. Either way, the universe has spoken, and we are listening. The silence of space has been broken by a whisper, and that whisper may carry the answer to the oldest and most profound question we have ever dared to ask. The mystery of the signal is a powerful reminder that our search is not just for planets and stars, but for meaning, for connection, for a sign that in this vast, dark expanse, There is another mind looking back at us, wondering, just as we are, about the nature of it all. While the grand cosmic narratives of time, space, and life are being rewritten on the largest scales, Webb has also turned its golden eye to our own galactic neighborhood, and what it has found there is no less revolutionary. In a star system surprisingly close to our own, it has discovered a world that feels hauntingly familiar, a planet, nestled squarely in its star's habitable zone, that is not just a rocky sphere, but a world with an atmosphere, a world with weather, a world that may hold liquid water. The initial analyses of this planet's atmosphere have been nothing short of breathtaking, using a technique called transit spectroscopy, where the telescope measures the starlight filtering through the planet's atmosphere as it passes in front of its star. Webb has detected the unmistakable chemical fingerprints of carbon, oxygen, and, most excitingly, water vapor. These are the fundamental ingredients for life as we know it. But it is the combination and the ratios of these gases that have truly captured the scientific community's imagination. The presence of both oxygen and methane in the same atmosphere is particularly significant. These two gases are chemically reactive and, on geological timescales, should destroy each other. On Earth, the only reason we have a stable, oxygen-rich atmosphere with traces of methane is because life is constantly replenishing them. Photosynthesis pumps out oxygen, while biological decay and digestion produce methane. Finding this specific chemical disequilibrium on another world is one of the strongest potential biosignatures we could hope for. It is not yet definitive proof of life. There could be unknown geological or photochemical processes that mimic biology, but it is a flashing green light, an invitation to look closer. NASA is now dedicating a significant portion of Webb's observational time to this single world, hoping to build a detailed map of its atmospheric composition, to search for seasonal variations that could indicate a global biosphere, and to even try and detect the glint of sunlight off a potential ocean, a phenomenon known as glints. The discovery of this world has moved the search for extraterrestrial life from the realm of abstract probability to a tangible, scientific quest with a specific target. It has also brought the dream of human expansion into sharper focus. While interstellar travel remains the stuff of science fiction, the existence of a potentially habitable world so close by provides a powerful, aspirational goal for future generations. It raises profound questions about our long-term survival and our responsibilities as a species. If we find life there, do we have the right to interfere? If we find it to be sterile, do we have the right to colonize it, to turn it into a second Earth? These are no longer just philosophical thought experiments, they are becoming practical, ethical dilemmas that we may have to face in the coming centuries. The discovery of this pale blue dot in a nearby star system is a mirror held up to our own world. It reminds us of the preciousness and fragility of our own biosphere, and it challenges us to become a species worthy of a cosmic destiny. The light from this nearby world tells us that planets like ours may not be a cosmic rarity, and that the conditions for life may be more common than we ever thought. It is a message of hope, a whisper from a neighboring shore that suggests we may not be the only ones to look up at the stars and wonder. And in a universe that often feels vast, cold, and indifferent, that message of hope may be the most important discovery of all. The search for life beyond Earth is also a search for ourselves, for our place in the grand tapestry. And this nearby world has just given us the most promising thread we have ever found. The fabric of our cosmic understanding, woven from threads of theory and observation, is being stretched to its breaking point not just by the unexpected maturity of the early universe, but by the very dynamics of its expansion. For decades, the Hubble constant, the measure of how fast the universe is expanding, has been a cornerstone of cosmology. It is the key that unlocks the universe's age, its size, and its ultimate fate. But it is a key that no longer seems to fit the lock. There is a crisis in cosmology, a growing and persistent tension between two different, highly precise methods of measuring this fundamental constant. The first method looks at the late universe. It uses objects with known intrinsic brightness, like Cepheid variable stars and Type Ia supernovae, as standard candles. By measuring how dim these candles appear from Earth, we can calculate their distance, and by measuring their redshift, the stretching of their light as they move away from us, we can calculate their speed. This method, refined over decades, and now honed to an incredible precision by telescopes like Hubble and Webb, gives us a value for the expansion rate of the local universe. The second method looks at the early universe. It studies the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The tiny temperature fluctuations in the CMB contain a wealth of information about the universe's initial conditions, its density, its composition, and its initial rate of expansion. By plugging these initial conditions into our standard cosmological model, called lambda CDM, we can predict what the expansion rate should be today. And here is the crisis: the two numbers do not match. The late universe measurement suggests the universe is expanding about 9% faster than the early universe prediction. This is not a small rounding error, it is a 5 sigma discrepancy, a statistical level that in particle physics would be hailed as a definitive discovery. Something is fundamentally wrong. Either our measurements are flawed in some subtle, systematic way we do not understand, or our standard model of cosmology, the theory that has guided our understanding for a generation, is incomplete. Webb's role in this crisis is pivotal. Its incredible resolution allows it to measure the standard candles in the late universe with unprecedented accuracy, eliminating many of the potential sources of error that have plagued previous measurements. And its initial findings have not resolved the tension, they have sharpened it. The faster expansion rate appears to be real. This forces us to confront the possibility that our lambda CDM model is missing a key ingredient. The model is built on just a few key components: normal matter, and dark energy. But what if there is something else? Perhaps there was a period of early dark energy, a new form of energy that was present in the first few 100,000 years of the universe's life, which gave the cosmos an extra kick of expansion before it dissipated. This would change the initial conditions inferred from the CMB, potentially bringing the early and late universe measurements into alignment. Or perhaps dark matter is not as simple as we think. Maybe it is not a single inert particle, but a whole family of particles with complex interactions that have changed over cosmic time. A different behavior of dark matter in the early universe could alter the way sound waves propagated through the primordial plasma, which would in turn change our interpretation of the CMB data. Even more radically, some physicists have proposed that Einstein's theory of general relativity itself may need to be modified on cosmological scales. While it works perfectly in the solar system and for phenomena like gravitational lensing, it is possible that on the scale of the entire universe, gravity behaves differently, leading to a different expansion history. This is a path most scientists are reluctant to take, as general relativity is one of the most successful and well-tested theories in the history of science, but the persistent Hubble tension is forcing us to consider even the most outlandish possibilities. The resolution of this crisis, whatever it may be, will mark a new era in cosmology. It will either reveal a new component of the universe, a new law of physics, or a new understanding of our cosmic history. Webb is at the heart of this investigation, providing the crucial, high-precision data that will either break the standard model or reveal the subtle flaw in our measurements that has led us astray. The faster expansion rate is not just a number, it is a clue, a breadcrumb leading us into a deeper, richer, and more complex understanding of the universe. It tells us that the cosmic story is still unfolding, and that there are new chapters, perhaps even new characters, that we have yet to discover. The universe is not just expanding, it is expanding in a way that challenges our deepest theories, forcing us to be more creative, more rigorous, and more open-minded in our quest to understand its ultimate nature. The implications of this accelerated expansion ripple outwards, touching not just the beginning of the universe, but its ultimate end. The fate of the cosmos is intimately tied to the nature of dark energy, the mysterious force that appears to be driving this expansion. In our standard model, dark energy is represented by the cosmological constant, an intrinsic energy of space-time itself. In this scenario, the density of dark energy remains constant as the universe expands. As matter and radiation become more dilute, dark energy becomes the dominant component of the universe's energy budget, leading to an endless, accelerating expansion. The ultimate fate in this model is a heat death or big freeze. Galaxies will recede from each other until they are so far apart that their light can no longer reach us. The sky will become dark, empty, and cold. The last stars will burn out, their fuel exhausted. Black holes will slowly evaporate over trillions of years through Hawking radiation. The universe will settle into a final state of maximum entropy, a cold, uniform, and eternal darkness, where nothing ever happens again. It is a bleak, but scientifically plausible, end. However, the data from Webb, suggesting a faster than expected expansion, opens the door to other, more dramatic possibilities. What if dark energy is not a constant? What if its density is increasing over time? This hypothetical form of energy is known as phantom energy, and it leads to a far more violent end, the Big Rip. In this scenario, the repulsive force of dark energy will eventually become so strong that it will overcome all other forces in the universe. In the final moments of the cosmos, billions of years from now, the ever-increasing dark energy will first tear apart the great galaxy clusters. Then, it will unbind the galaxies themselves, flinging their stars into the void. As the end approaches, the force will become strong enough to overcome the gravity holding solar systems together, separating planets from their stars. Then, it will overcome the electromagnetic force, tearing the planets and stars themselves apart. In the final fraction of a second, it will overcome the strong nuclear force, ripping apart the atomic nuclei, reducing the entire universe to a shower of fundamental particles, each isolated from the others in an infinitely expanding void. The very fabric of space-time would be torn asunder. Webb's precise measurements of the expansion history of the universe are crucial to distinguishing between these scenarios. By looking at distant supernovae and the distribution of galaxies over cosmic time, it can help us determine the equation of state of dark energy, a parameter that tells us how its pressure relates to its density. If this parameter is exactly -1, it points to a cosmological constant and a big freeze. If it is less than -1, it points to phantom energy and a big rip. While current data is still consistent with a cosmological constant, the hints of a faster expansion keep the door open for these more exotic and more terrifying possibilities. There are other, less talked about scenarios as well. The Big Slurp, for instance, arises from the idea that our universe's vacuum state is not truly stable, but only metastable. It is like a ball resting in a small divot on the side of a large hill. It is stable for now, but a sufficient jolt could send it rolling down to a much lower true vacuum state. If a bubble of this true vacuum were to nucleate somewhere in the universe, it would expand at the speed of light, converting our universe into this new state as it went. The laws of physics, the fundamental constants, the very particles that make up our existence, would all be different inside this bubble. It would be the ultimate phase transition, and we would not see it coming. Our end would be instantaneous and absolute. Webb contributes to this line of inquiry by studying the most energetic events in the universe, searching for any sign of physics that deviates from our standard model, any hint that the vacuum of space-time is not as stable as we assume. The end of the universe is no longer a topic confined to theology or philosophy. It is a field of active, data-driven scientific research. The images Webb captures are not just snapshots of the past. They are frames in a cosmic movie. And by studying them carefully, we are beginning to glimpse the final scene. It is a profoundly human endeavor to seek to understand not just our origins, but our ultimate destiny. And Webb is our most powerful tool in this existential quest. The invisible components of the cosmos, dark matter and dark energy, do not just dictate its ultimate fate, they are the architects of its present tensed structure. Dark matter, comprising roughly 85% of the matter in the universe, is the silent, unseen majority. It does not emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, we know it is there. We see its gravitational influence everywhere we look. We see it in the rotation curves of galaxies, where the outer stars are moving far too fast to be held in orbit by the visible matter alone. We see it in the gravitational lensing of distant light, where the gravity of massive galaxy clusters, far greater than their visible mass could account for, bends and distorts the light from objects behind them, acting like a cosmic magnifying glass. And we see it in the large-scale structure of the universe, the cosmic web of filaments and voids, which could not have formed without the gravitational scaffolding of dark matter. Webb is revolutionizing the study of dark matter by providing the most detailed and precise maps of its distribution ever created, by meticulously analyzing the distorted shapes of thousands of background galaxies in its deep field images, a technique called weak gravitational lensing. Astronomers can reconstruct the invisible mass distribution of the foreground clusters. These new maps are revealing a picture of dark matter that is both beautifully consistent with our models and subtly challenging. On the one hand, they confirm that dark matter is distributed in vast, extended halos around galaxies and clusters, providing the gravitational glue that holds them together. But on the other hand, the cores of some of these dark matter halos appear to be less dense, or cuspier, than our simplest cold dark matter simulations predict. The CDM model assumes that dark matter particles are slow-moving and interact only through gravity. This discrepancy could be a sign that dark matter is more complex than we thought. Perhaps it is not cold, but warm, meaning the particles had higher velocities in the early universe, which would smooth out the density cusps in the centers of halos. Or, more intriguingly, perhaps dark matter interacts with itself through some unknown force, a dark force that operates only in the dark sector. These self-interactions could cause the dark matter particles to scatter off each other, effectively heating up the core of the halo and reducing its density. Webb's data is providing crucial ammunition for these debates. Furthermore, by observing the aftermath of galaxy cluster collisions, like the famous bullet cluster, Webb can study how dark matter behaves under extreme conditions. In these collisions, the hot gas of the two clusters crashes together and slows down, while the stars and the dark matter, interacting only weakly, pass right through each other. Webb's ability to map both the hot gas and the dark matter allows for a precise test of the self-interaction cross-section of dark matter. So far, dark matter appears to be remarkably collisionless, which puts tight constraints on many of the more exotic self-interacting models. The quest to identify the dark matter particle is one of the great unfinished revolutions in physics. It is a puzzle that connects the largest structures in the universe with the world of particle physics. While Webb cannot detect the dark matter particle directly, its detailed observations of the universe's structure are providing crucial, indirect clues that will guide the design of the next generation of particle detectors here on Earth. By studying the grand architecture of the cosmos, Webb is helping us to close in on the identity of its invisible architect. It is a testament to the power of astronomy that by looking out at the vastness of space, we can learn something fundamental about the subatomic world. Just as Webb is refining our understanding of the cosmic structure, it is also forcing us to reconsider the very process of creation within that structure, the formation of planets. The classic model of planet formation, the core accretion model, is a story of patient, steady growth. It begins with a young star surrounded by a protoplanetary disk, a spinning platter of gas and dust. Within this disk, tiny dust grains, coated in ice, begin to stick together. Through electrostatic forces, they form larger and larger aggregates, growing from pebbles to rocks, from rocks to boulders, and from boulders to planetesimals, kilometer-sized bodies that are the building blocks of planets. These planetesimals then continue to grow through gravitational encounters, their gravity pulling in more and more material, eventually forming the solid cores of planets. For gas giants like Jupiter, this core must grow to about 10 Earth masses quickly enough to gravitationally capture a massive atmosphere from the surrounding gas disk before the disk dissipates. A process that takes a few million years. It is a neat, orderly, and slow process. Webb's observations of protoplanetary disks, however, are painting a much more chaotic, dynamic, and complex picture. Its infrared vision can pierce through the obscuring dust and see the intricate structures within these planetary nurseries with unprecedented detail. It has revealed disks that are not smooth, continuous platters, but are carved with gaps, rings, and spiral arms. These structures are thought to be the signposts of forming planets, their gravity clearing out paths in the disk as they orbit the star. But the complexity and sharpness of these structures are challenging our models. Some gaps are too wide, some rings too narrow, to be explained by a single, peacefully accreting planet. This suggests that multiple planets may be forming in close proximity, their gravitational interactions creating a much more dynamic and turbulent environment. Moreover, Webb has discovered that the chemistry within these disks is far richer and more complex than we ever imagined. It has detected a zoo of complex organic molecules, including the building blocks of alcohols, aldehydes, and even simple sugars, frozen onto the surfaces of dust grains. This means that the raw ingredients for life are not just present, but abundant in the very places where new Earth-like planets are being born. This has profound implications for the theory of panspermia, the idea that life on Earth may have been seeded by organic material delivered by comets and asteroids that formed in our own solar system's protoplanetary disk. Webb's data suggests that this is not just a possibility, but a probability. But Webb has also uncovered a potential roadblock to this creative process. It is observed that the intense radiation from some young, active stars can create a hostile environment in the inner regions of their protoplanetary disks. This high-energy radiation can photoevaporate the gas, effectively blowing away the raw material needed for planet formation. It has also detected incredibly strong magnetic fields threaded through these disks, which can create dead zones where turbulence is suppressed, preventing dust grains from clumping together. This suggests that planet formation is a far more precarious process than we thought, a delicate balance between the creative forces of gravity and chemistry and the destructive forces of stellar radiation and magnetic fields. The universe may be teeming with the ingredients for planets, but the ovens in which they are baked are not all set to the right temperature. This finding could help explain why. Despite the vast number of stars, potentially habitable planets may still be rare. Webb is transforming planet formation from a story of slow, steady accumulation into a dramatic tale of cosmic weather, chemical complexity, and a constant battle between creation and destruction. It is showing us that the birth of a world like ours is not an inevitability, but the result of a precise and fortunate set of circumstances, a cosmic lottery that we were lucky enough to win. The cosmic lottery extends not just to the formation of planets, but to the very potential for life to take root and flourish upon them. Webb's unparalleled ability to analyze the atmospheres of exoplanets is ushering in a new era of comparative planetology, one where we can begin to understand the full diversity of worlds that the universe has to offer. And in this diversity, we are finding hints that the conditions for life may be both more widespread and more challenging than we had imagined. The discovery of potential biosignatures, like the combination of oxygen and methane on a nearby exoplanet, has rightfully captured the public's imagination. But Webb is also finding worlds that defy our expectations and challenge our definitions of habitability. It has studied Hycean worlds, a new class of planet that is larger than Earth but smaller than Neptune, with a deep global ocean covered by a thick hydrogen-rich atmosphere. Theoretically, life could exist in these oceans, but it would be a very different kind of life, adapted to high pressures and an environment devoid of a rocky surface. Webb's initial observations of these worlds have detected water vapor, but also hints of molecules like dimethyl sulfide, which on Earth is produced almost exclusively by marine phytoplankton. This is an incredibly tantalizing, though highly preliminary, clue that these exotic water worlds might harbor vast, hidden biospheres. At the same time, Webb has also provided cautionary tales. It has studied the atmospheres of planets orbiting red dwarf stars, the most common type of star in the galaxy. For a long time, these stars were considered prime targets in the search for life, as their long lifespans and stable energy output would seem to provide a perfect environment for life to evolve. However, Webb has revealed that many planets orbiting close to these stars, in their habitable zones, have been stripped of their atmospheres. Young red dwarfs are notoriously active, unleashing powerful stellar flares and intense ultraviolet radiation that can erode a planet's atmosphere over time, leaving it a barren, airless rock. This suggests that the habitable zone is not just about temperature, it is about the complex interplay between a planet's magnetic field, its atmospheric composition, and the violent nature of its host star. The universe may be full of planets in the right place, but many of them may have been sterilized by their own suns. Webb is also revolutionizing our understanding of our own solar system's history by studying the composition of asteroids and comets. It has confirmed the presence of complex organic molecules, including amino acids, on asteroids, lending strong support to the idea that the building blocks of life were delivered to the early Earth from space. By analyzing the isotopic ratios of water in comets, it is helping us to trace the origin of Earth's oceans. These observations are blurring the line between geology, chemistry, and biology, showing us that the story of life on Earth is inextricably linked to the history of the cosmos. The emergence of life is not a separate event, but a continuation of the same cosmic processes that form stars and planets. It is a story of cosmic chemistry, of stellar evolution, of galactic dynamics. And as Webb continues to collect these chemical fingerprints from distant worlds, it is compiling the first ever galactic census of habitability. It is a monumental task, and one that may not yield a definitive answer in our lifetimes. But for the first time, we have the tool to conduct the search in a systematic, scientific way. We are moving beyond speculation and into the realm of data. We are no longer just asking, are we alone? We are gathering the evidence that will one day provide the answer. It is a quest that is as much about understanding the universe as it is about understanding ourselves. For in the search for life elsewhere, we are forced to confront the very definition of life, the conditions that make it possible, and the profound and perhaps unique circumstances that led to our own existence. The universe as revealed by the James Webb Space Telescope is not only a place of unexpected creation and complex chemistry, but also of raw, untamed violence. The serene, clockwork cosmos of Newton has been replaced by a dynamic and often ferocious reality, where cosmic cataclysms are not rare exceptions, but fundamental drivers of cosmic evolution. Webb's infrared eyes have given us an unprecedented, ringside seat to some of the most energetic events in the universe, and these observations are challenging our understanding of stellar life cycles, galactic dynamics, and the very limits of physical law. For instance, the telescope has captured images of massive star collisions with a clarity that is both beautiful and terrifying. When two stars in a binary system spiral into each other and merge, the resulting explosion, known as a luminous red nova, can temporarily outshine an entire galaxy. Webb's observations have shown that these events are not just about the release of energy, they are powerful chemical factories. The shock waves from the collision create extreme temperatures and pressures, forging a host of heavy elements and flinging them out into the interstellar medium. But what has truly surprised astronomers is the sheer frequency and diversity of these stellar mergers. They appear to happen more often than our models predicted, suggesting that close binary star systems are more common, or their orbital decay is more rapid than we previously thought. This has significant implications for our understanding of gravitational waves, as merging neutron stars and black holes, the compact remnants of massive stars, are the primary sources for detectors like LIGO and Virgo. Webb's ability to identify the host galaxies of these mergers and study the aftermath of the explosion provides a crucial counterpart to the gravitational wave data, allowing for a much richer, multi-messenger understanding of these extreme events. But it's not just the violence between stars that Webb is uncovering, it's the violence within them. The telescope has observed unexpected, massive explosions on the surfaces of stars that were thought to be in stable phases of their life. These are not the final death throes of a supernova, but powerful eruptions on otherwise ordinary stars, some of them relatively close to Earth. These events, akin to solar flares but thousands of times more powerful, release vast amounts of energy and high-energy particles into their surrounding systems. The cause of these superflares is still being debated, but it likely involves the complex twisting and snapping of magnetic field lines in the star's atmosphere. The fact that they are occurring on stars not previously considered to be so active has become a cause for concern. It suggests that the space weather around other star systems could be far more extreme and unpredictable than we had assumed. This has direct implications for the habitability of exoplanets, a planet orbiting a star prone to such superflares, even if it is in the habitable zone, would be repeatedly bathed in lethal radiation, its atmosphere stripped away, and its surface sterilized. The search for life, therefore, must now include a search for stellar tranquility. A quiet sun may be just as important as a watery world. This new understanding of stellar violence is forcing a re-evaluation of cosmic risk. While the chances of a nearby star unleashing a superflare powerful enough to directly impact Earth are incredibly low, they are not zero. Webb's observations serve as a stark reminder that we live in a dynamic, and sometimes dangerous, cosmic neighborhood. The universe is not a benign and peaceful place. It is a stage for a constant drama of creation and destruction, and we are just beginning to appreciate the full scale of its power. The drama of cosmic violence reaches its zenith in the heart of galaxies, where supermassive black holes reign, these gravitational monstrosities, with masses millions or even billions of times that of our Sun, were once thought of as passive eaters, silently swallowing any matter that strayed too close. Webb has shown this picture to be woefully incomplete. Its observations of galactic centers have revealed them to be regions of astonishing and chaotic activity, cosmic storms of unparalleled intensity. The supermassive black hole at the center of our own Milky Way, Sagittarius A, was long thought to be relatively quiescent, but Webb has detected flares and outflows of hot gas from its immediate vicinity, suggesting that it is not dormant, but merely napping, periodically waking to feed on nearby stars and gas clouds. When this material spirals into the black hole, it forms an accretion disk, a swirling vortex of matter heated to millions of degrees, which glows intensely in the infrared. But not all of this matter is consumed. Powerful magnetic fields, generated by the spinning black hole and the accretion disk, can launch a portion of this material outwards in highly collimated jets that travel at nearly the speed of light. These jets can extend for thousands of light years, plowing through the host galaxy and carving out vast cavities in the interstellar medium. This process, known as galactic feedback, is now understood to be one of the most important mechanisms in regulating the growth of galaxies. The energy and radiation pumped out by an active black hole can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. This effectively quenches star formation in the galactic core, and can even halt the growth of the galaxy as a whole. Webb has observed this process in action in distant galaxies, imaging the vast outflows of molecular gas being driven out of galactic centers by the power of their central black holes. It has shown that black holes are not just sinks of matter, they are cosmic engines, powerful thermostats that dictate the fate of their entire host galaxy. This discovery helps to solve a long-standing puzzle in astronomy. Why are the most massive galaxies not even bigger? Our models of hierarchical formation predicted that galaxies should just keep growing as they merge with others. But what we observe is that the most massive galaxies seem to have stopped forming stars billions of years ago. Galactic feedback from their supermassive black holes provides the perfect explanation. Once the black hole grows large enough, it effectively sterilizes its host galaxy, preventing any further growth. This intimate, and often violent, coevolution of black holes in galaxies is a new and exciting frontier in astrophysics, and Webb is providing the key data to unlock its secrets. By studying the relationship between the mass of a black hole and the properties of its host galaxy across cosmic time, we can begin to piece together the history of this cosmic dance, a dance that has shaped the very structure and appearance of the universe we see today. The centers of galaxies are not places of quiet solitude, they are the thundering hearts of the cosmos, where the most extreme forces of nature are at play, shaping the destinies of trillions of stars and worlds. Beyond the chaos of galactic cores and stellar explosions, Webb has also turned its gaze to the vast, seemingly empty chasms of the universe, the great cosmic voids. These are the largest and most underdense regions of the cosmos, vast deserts of space-time containing almost no galaxies, stars, or gas. In the standard picture of the cosmic web, these voids are the natural consequence of gravity. As matter clumps together to form filaments and clusters, it leaves behind these vast empty regions. They were thought to be simple, boring, and largely devoid of interest. Webb, however, has revealed that even the emptiness is not what it seems. During its deep space observations, the telescope has discovered an incredibly large cosmic void, a region of space hundreds of millions of light years across that is even emptier than our models predicted. The sheer scale and emptiness of this void are difficult to explain. It is as if a giant cosmic bubble was inflated in the early universe, pushing all the matter to its edges. One possible explanation is that this void is the result of a particularly large negative density fluctuation in the primordial universe, a region that started out with slightly less matter than average and has been growing ever since, as its weak gravity has been unable to compete with the overall expansion of the universe. But the scale of this void hints at something more. Some cosmologists have speculated that such voids could be the imprint of another universe bumping into ours in the context of the multiverse. In some versions of eternal inflation, our universe is just one bubble in a vast, eternally inflating space-time, and collisions between these bubble universes are possible. Such a collision would leave a bruise on our CMB, a circular cold spot, and could trigger a large-scale outflow of matter, creating a vast void. While highly speculative, the existence of such a giant void provides a potential, albeit circumstantial, piece of evidence for this extraordinary idea. But even within the voids, Webb has found unexpected surprises in what were thought to be the darkest, most desolate regions of space. Webb has discovered faint, isolated objects, shining where nothing should be shining. These are not normal stars or galaxies. Their light signatures, their spectra, do not match any known celestial object. They are too small and too isolated to be dwarf galaxies, and too bright to be single stars. Their nature is a complete mystery. Could they be a new type of object? Perhaps primordial black holes formed in the first second of the universe's existence, surrounded by a faint halo of captured gas that is slowly accreting onto them? Or could they be evidence of a more exotic form of matter? Perhaps dark stars powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. The existence of these void objects challenges our understanding of structure formation. It suggests that even in the most underdense regions of the universe, pockets of matter can collapse and form luminous objects, a process our current simulations struggle to reproduce. The voids are no longer the boring, empty parts of the cosmic map. They are a new frontier for discovery, a laboratory for testing our understanding of gravity, dark matter, and the very initial conditions of the universe. They are a reminder that the universe is full of secrets, not just in the bright, crowded hearts of galaxies, but also in its darkest, most solitary corners. The emptiness speaks, and Webb is the first to truly hear its voice. The universe's inventory of the strange and the new is not limited to its largest structures or most violent events. It extends down to the very building blocks of matter and the forces that govern them. Webb's high-precision measurements are probing the universe with a sensitivity that allows us to test the fundamental laws of physics in ways that are impossible in terrestrial laboratories. And in these tests, we are beginning to see faint, but persistent, hints of new physics beyond our standard model. One of the most intriguing of these is the detection of the strongest magnetic field ever observed in the universe. This field, millions of times stronger than anything we can generate on Earth, was found surrounding a magnetar, a type of neutron star with an incredibly powerful magnetic field. But the field observed by Webb extends over a much larger region of space than the neutron star itself, suggesting a more complex and previously unknown structure. The sheer strength of this field is pushing the limits of our understanding of magnetohydrodynamics, the physics of electrically conducting fluids. How such a field is generated and sustained is a major puzzle. It may be a remnant of the magnetic field of the progenitor star, amplified to an incredible degree during the collapse of its core in a supernova. Or it may be generated by a dynamo mechanism within the rapidly spinning neutron star, a process that is still not fully understood. The existence of such an extreme magnetic field has profound implications. These fields can influence the paths of high-energy cosmic rays. They can affect the process of star formation in their vicinity, and they can even, in theory, cause the vacuum of space itself to become birefringent, meaning it would affect the polarization of light passing through it, a prediction of quantum electrodynamics that has yet to be observed. Webb's discovery provides a new laboratory for studying physics under the most extreme conditions imaginable, conditions that we can never hope to replicate on Earth. But Webb's search for new physics is not just about finding the extreme, it is also about finding the subtle. The telescope's precise measurements of the chemical composition of the oldest stars in the universe are providing a crucial test of Big Bang nucleosynthesis, the theory that predicts the primordial abundances of the light elements like hydrogen, helium, and lithium. While the theory has been remarkably successful, there has been a long-standing lithium problem. The observed abundance of lithium in old stars is about 3 times lower than the theory predicts. Webb's ability to get clean, high-resolution spectra of these ancient stars is helping to clarify this issue. It is possible that the discrepancy is not a flaw in the Big Bang theory, but is due to stellar processes that destroy lithium in the outer layers of these stars over their long lifetimes. By studying stars of different ages and temperatures, Webb can help to disentangle the primordial abundance from the effects of stellar evolution. However, if the discrepancy persists, even after accounting for these effects, it could be a sign of new physics in the early universe, perhaps related to the decay of a new particle or a modification to the laws of thermodynamics at high temperatures. These are subtle, painstaking measurements, far from the headline-grabbing images of beautiful nebulae, but they are at the heart of Webb's scientific mission. It is in these subtle deviations from our expectations, these small cracks in the facade of our standard models, that the seeds of the next revolution in physics are often found. The universe is a vast and complex place, and it is through the combined power of observing the grand and measuring the minute that we can hope to piece together its deepest secrets. The tapestry of cosmic discovery being woven by Webb is not just composed of threads of light and gravity, but also of the complex, life-giving molecules that drift in the spaces between the stars. The telescope has revolutionized the field of cosmic chemistry, revealing that the interstellar medium is a far richer and more complex chemical laboratory than we ever knew. Its infrared spectrographs can identify the telltale absorption and emission lines of specific molecules with incredible sensitivity, allowing us to take a chemical inventory of the universe. And that inventory has been full of surprises. Webb has confirmed the widespread presence of polycyclic aromatic hydrocarbons, complex carbon-based molecules that on Earth are often associated with the byproducts of combustion, like soot. In space, however, they are thought to form in the cool, carbon-rich atmospheres of dying stars and are then spread throughout the galaxy. These molecules are incredibly important, as they are thought to play a crucial role in the heating and cooling of the interstellar medium, and may even act as catalysts for the formation of more complex molecules. But what has been truly astonishing is the sheer variety and complexity of the organic molecules that Webb is finding. In the dense, cold molecular clouds where new stars and planets are born, Webb has detected the signatures of not just simple molecules like water and carbon monoxide, but also more complex species like methanol, ethanol, and acetic acid, the main component of vinegar. These are not just random molecules, they are the building blocks of the more complex organic chemistry that leads to amino acids, sugars, and the other components of life. The fact that they are forming in these cold, dark clouds, even before the birth of a star, suggests that the universe has a natural tendency towards chemical complexity. The process is thought to begin with simple molecules freezing onto the surfaces of tiny dust grains, forming an icy mantle. Within this ice, the faint ultraviolet light from distant stars can trigger a series of chemical reactions, breaking apart the simple molecules and allowing them to recombine into more complex forms. Over millions of years, this slow, cold chemistry builds up a rich inventory of organic material. When a new star and protoplanetary disk form from the collapse of this cloud, this organically rich material is incorporated into the comets and asteroids that will eventually deliver it to the young planets. Webb's observations have provided the most direct evidence yet for this entire process. It has imaged the icy mantles on dust grains. It has identified the complex organic molecules within those ices, and it has detected the same molecules in the inner regions of protoplanetary disks, right where new Earths are forming. It is a beautiful, coherent story that connects the chemistry of the interstellar medium directly to the origins of life. The universe, it seems, is not just littered with the ingredients for life, it has a well-established supply chain for delivering them. This has profound implications for our understanding of our own origins. It suggests that the emergence of life on Earth was not a fluke, a 1 in a trillion chemical accident, but was perhaps the natural, and maybe even inevitable, outcome of a universal process of chemical evolution. This perspective, known as cosmic gradualism, shifts the focus from a single, miraculous spark of life to a long, continuous chain of events, stretching from the cold hearts of molecular clouds to the warm oceans of young planets. We are not just star stuff. As Carl Sagan famously said, we are the product of a cosmic chemistry that has been unfolding for billions of years, a chemistry that Webb is now allowing us to witness in its full glory for the very first time. The universe that the James Webb Space Telescope is unveiling is not just a physical space of stars and galaxies, it is also a philosophical landscape that forces us to confront our most fundamental assumptions about reality, existence, and our own place in the cosmos. Every image, every data point, is not just a piece of a scientific puzzle, but also a mirror reflecting our own curiosity, our own finitude, and our own search for meaning. The discovery of galaxies that are older and more mature than our theories predicted does not just challenge our models of cosmology, it challenges our sense of temporal progression and our place within it. We have a natural human tendency to see our own time, our own planet, our own galaxy as somehow special, as the culmination of a long evolutionary process. But Webb's data suggests that the universe was capable of creating complexity and order much earlier than we thought. Our Milky Way is not the venerable elder we imagined, but perhaps just one of many, a late bloomer in a cosmos that was already teeming with grand galactic structures. This is a profound lesson in cosmic humility. It decenters humanity not just from the center of the solar system, as Copernicus did, or from the center of the galaxy, as Shapley did, but from a privileged position in cosmic time itself. We are not the pinnacle of cosmic evolution. We are an eddy in a river that has been flowing for a long, long time, a river that has seen other, perhaps grander, civilizations rise and fall before our sun was even born. This realization can be both unsettling and liberating. It is unsettling because it removes any sense of cosmic specialness, any notion that the universe was somehow designed with us in mind, but it is liberating because it opens up the vast expanse of cosmic history to the possibility of others. The universe is not a story that leads only to us. It is a grand, sprawling epic with countless protagonists, and we have only just begun to read its opening chapters. This perspective forces us to think on truly geological and even cosmological timescales. The challenges we face as a species, climate change, political conflict, resource depletion, can seem insurmountable on a human timescale, but when viewed against the backdrop of a universe that is at least 13.8 billion years old, and perhaps much older, our problems, and indeed our entire existence, are but a fleeting moment. This does not mean they are insignificant. On the contrary, it highlights the incredible preciousness and fragility of this conscious moment we have been given. The universe has been here for an immense amount of time, and will likely be here for an immense amount of time to come. The question is, will Webb's images are a silent, powerful call to a longer-term perspective, a perspective that transcends national borders, political ideologies, and even the lifespan of our species. They invite us to see ourselves as part of a much larger, much older story, and to act with the wisdom and foresight that such a perspective demands. The philosophical implications deepen when we consider the search for extraterrestrial life, a search that Webb has transformed from a speculative exercise into a data-driven science. The detection of potential biosignatures in the atmosphere of a nearby exoplanet is a scientific milestone, but it is also a philosophical bombshell waiting to explode. The confirmation of life beyond Earth, even microbial life, would be the most profound discovery in the history of science, a discovery that would fundamentally reshape our understanding of ourselves and our place in the universe. For millennia, humanity has looked up at the stars and asked, "Are we alone?" This question is at the heart of our religions, our mythologies, and our scientific inquiries. It is a question about uniqueness, about purpose, and about our ultimate cosmic significance. To find that the answer is no, that life is not a unique miracle confined to our own small world, would be to complete the Copernican revolution. It would be the final step in the long, and often painful, process of removing humanity from the center of creation. But what would the discovery of life, particularly intelligent life, actually mean for us? On the one hand, it could be a source of immense hope and inspiration. The knowledge that we are not alone, that consciousness is a phenomenon that has arisen independently elsewhere, would provide a powerful sense of connection to the cosmos. It would suggest that the universe is not a sterile, meaningless void, but is, in some fundamental way, life-friendly, even consciousness-friendly. It could also provide a powerful impetus for global unity. The realization that we are all Earthlings, members of one of many cosmic civilizations, could help to dissolve the petty national and cultural divisions that have plagued our history. The overview effect experienced by astronauts, a profound cognitive shift in awareness that comes from seeing the Earth as a fragile, unified whole floating in the void, could become a shared experience for all of humanity. On the other hand, the discovery of intelligent life could also be a source of profound existential dread. The Fermi paradox. The apparent contradiction between the high probability of extraterrestrial life and the lack of any evidence for it has long haunted our search. One possible solution to the paradox is the Great Filter, a hypothetical evolutionary or technological hurdle that is so difficult to overcome that it prevents almost all civilizations from reaching a stage where they can communicate or travel between the stars. The filter could be behind us or it could be ahead of us. If we were to detect the ruins of a long-dead alien civilization, it would be a chilling discovery. It would suggest that the Great Filter is still in our future, a silent warning that our own technological prowess may be the instrument of our own doom. Webb's observations, while not yet capable of detecting alien artifacts, are providing the first statistical data on the prevalence of potentially habitable worlds. This data will help us to better constrain the variables in the Drake equation, the famous probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Every new Earth-like planet discovered increases the probability of life, but it also deepens the mystery of the Great Silence. We are living in a unique moment in history, a moment where a question that was once the sole domain of philosophers and priests is now being addressed with the rigorous tools of science. The answer, whatever it may be, will have a profound and lasting impact on the future of human thought. The universe that Webb is revealing is not just challenging our place in time and our uniqueness in the cosmos, it is also challenging our very understanding of reality itself through its observations of the invisible. The confirmation of the existence and distribution of dark matter and dark energy is not just a triumph of observational cosmology, it is a profound statement about the limits of human perception and the nature of knowledge. We have discovered that 95% of the universe is made of stuff that we cannot see, cannot touch, and cannot directly interact with. Our entire reality, everything we have ever known, the stars, the planets, ourselves, is just 5% of the cosmic inventory. We are the foam on the surface of a vast, dark ocean. This is a philosophical realization as much as a scientific one. It teaches us that the reality accessible to our senses is not the whole of reality. It is a powerful argument against a naive empiricism, the idea that what is real is only what can be directly observed. The existence of dark matter and dark energy was not discovered by seeing them. It was inferred through their effects on the things we can see. It is a triumph of reason, of our ability to build models, make predictions, and test them against the world. It shows that the human mind, through the language of mathematics and the process of science, can grasp realities that are forever beyond the reach of our biological senses. But this discovery also brings with it a deep sense of epistemological humility. It reminds us that our understanding of the universe is, and perhaps always will be, incomplete. If we were wrong about 95% of the universe's composition for most of our history, what else are we wrong about? What other fundamental components of reality are we currently blind to? The search for the nature of dark matter and dark energy is not just a scientific quest, it is a quest to understand the true substance of the world we inhabit. It forces us to confront the possibility that the universe is not just stranger than we imagine, but stranger than we can imagine. The very language and concepts we use to describe the world may be inadequate to the task of capturing its ultimate nature. Perhaps dark matter is not a particle in the traditional sense, but a manifestation of a higher dimensional reality, its gravitational influence leaking into our 3 dimensions of space. Perhaps dark energy is not an energy of the vacuum, but a sign that our understanding of gravity itself is flawed, a hint that the laws of physics are not constant, but are evolving along with the universe. These are speculative ideas, but they are the kind of ideas that are born in times of scientific crisis. When the data refuses to fit our established models, Webb is providing the data that is fueling this crisis. And in doing so, it is pushing us towards a new, and perhaps more profound, understanding of the cosmos. The discovery of the dark universe is not just about adding new items to our cosmic inventory. It is about fundamentally changing our relationship with reality, forcing us to accept our limitations and to embrace the deep and enduring mystery that lies at the heart of existence. This sense of mystery is amplified by the anomalies, the outliers, the observations that simply do not fit, the discovery of a massive cosmic wall, the detection of mysterious light signals, the observation of objects moving at incredible speeds. These are not just interesting astronomical curiosities, they are potential cracks in our edifice of knowledge, through which the light of a new understanding may be dawning. The cosmic wall, for example, is not just a challenge to the cosmological principle, it is a challenge to our understanding of causality and information in the early universe. How could a structure so large have formed? The speed of light imposes a fundamental limit on how quickly information and influence can travel. In the early universe, regions of space that are now billions of light years apart were not in causal contact with each other. They should have evolved independently. Yet, The existence of such a coherent, large-scale structure suggests that there may have been some form of superluminal connection or preordained correlation in the primordial universe. This is the same problem that the theory of cosmic inflation was invented to solve the horizon problem, and the cosmic wall may be telling us that our current theory of inflation is not the whole story. Similarly, the mysterious light signals, whether they prove to be natural or artificial, force us to confront the unknown. If they are natural, they represent a new type of astrophysical object or process, a new piece of the cosmic puzzle that will enrich our understanding of the universe's physics. If they are artificial, they represent something far more profound, the existence of another technological intelligence. This would raise a host of new philosophical and ethical questions. Should we respond? What would we say? How would the knowledge of their existence change our society, our religions, our sense of self? The search for extraterrestrial intelligence has often been on the fringes of mainstream science, but Webb's ability to detect atmospheric biosignatures and its potential to stumble upon anomalous signals is bringing it back into the heart of scientific inquiry. These anomalies are crucial to the progress of science. Science does not advance by only confirming what we already know. It advances by confronting what we do not know, by grappling with the data that does not fit. It is in the patient, rigorous, and open-minded investigation of these anomalies that the next great breakthroughs will be found. Webb is a powerful anomaly-generating machine. Its sensitivity and its unique observational window in the infrared are allowing it to see the universe in a new light, to uncover phenomena that were previously hidden from us. Each of these mysteries is an invitation, a call to adventure for the human mind. They are a reminder that the universe is not a closed book that we are close to finishing, but a vast, open library with an infinite number of volumes, most of which we have not even opened yet. The true value of an instrument like Webb is not just in the answers it provides, but in the new, deeper, and more profound questions it allows us to ask. It is a tool for expanding not just our knowledge, but our sense of wonder. The ultimate philosophical question that Webb's observations raise is about our own future, both as a species and as a part of a cosmic story. The telescope's data on the accelerating expansion of the universe and the potential for a Big Rip ending forces us to confront our own cosmic mortality. The idea that the universe itself has a finite, and potentially violent, end can be a source of existential angst. What is the meaning of our endeavors, our art, our science? If it is all destined to be torn apart in a cosmic cataclysm, this is not a new question. Philosophers and theologians have grappled with the problem of meaning in the face of mortality for centuries, but Webb is bringing this question into the realm of empirical science. We may, for the first time in history, be able to make a data-driven prediction about the ultimate fate of our reality. But this knowledge does not have to lead to despair. On the contrary, it can be a powerful source of meaning and purpose. The philosopher Bertrand Russell, in his essay A Free Man's Worship, argued that it is precisely in the face of a godless, indifferent, and ultimately doomed universe that humanity can find its true dignity. We must, he wrote, build our lives on the firm foundation of unyielding despair. But from that despair, we can create our own meaning, our own values, our own beauty. Webb's vision of a potentially finite universe can be seen in a similar light. The knowledge that our cosmic moment is fleeting can imbue it with a profound sense of preciousness. It can motivate us to make the most of the time we have, to cherish our planet, to foster compassion, and to pursue knowledge and beauty for their own sake, not for some eternal reward, but for the simple, profound value they have in the here and now. Furthermore, the hints of new physics, the anomalies in space-time, the potential for a deeper understanding of gravity, these also offer a glimmer of a different kind of hope. While still in the realm of extreme speculation, the idea that humanity could one day understand the laws of physics well enough to manipulate space-time, to travel between the stars, or even to survive the end of our own universe, is a powerful and enduring dream. Webb's discovery of potential space-time anomalies or natural tunnels is a long, long way from a warp drive, but it is a scientific data point that touches on this dream. It suggests that the universe may contain secrets and possibilities that could, in the far future, offer a path to a longer-term survival. This is not a prediction, it is an inspiration. It is a call to continue our quest for knowledge, not just to understand the universe, but perhaps one day to become active participants in its future. Webb's legacy, therefore, will not just be in the scientific papers it generates or the theories it rewrites. Its legacy will be in the way it shapes our collective human consciousness. It is a tool that allows us to see our origins, to contemplate our place in the cosmos, and to imagine our future. It is a source of humility, of wonder, and of a profound sense of connection to the vast and mysterious universe that has given us birth. In looking out, we are also looking in, and what we are finding is that the story of the cosmos is also, in the deepest sense, our own. The ongoing cascade of discoveries from the James Webb Space Telescope is not merely adding new chapters to our understanding of the cosmos, it is compelling us to fundamentally rethink the very processes of creation. From the birth of the first stars to the intricate assembly of planetary systems. We are moving from a static picture of cosmic evolution to a dynamic, and often violent, narrative where nothing is as simple as our previous models suggested. Webb's infrared vision has peeled back the dusty curtains of stellar nurseries, revealing the birth of stars in unprecedented detail. It has shown us that the process is not a gentle, uniform collapse of a gas cloud. Instead, it is a turbulent and chaotic affair, shaped by the complex interplay of gravity, magnetic fields, and powerful outflows of material from the young protostars themselves. These outflows, bipolar jets of gas traveling at hundreds of kilometers per second, are launched from the poles of the young star and plow into the surrounding molecular cloud, creating spectacular, glowing shockwaves. Webb has imaged these jets with stunning clarity, revealing intricate bow-shock structures and knots of heated gas. These observations are crucial because these outflows act as a form of stellar feedback, clearing away the surrounding material and ultimately limiting the final mass of the star. They are a key part of the self-regulation process that governs star formation across the galaxy. But Webb has also revealed a new puzzle. In some regions, it has observed that the formation of massive stars seems to be much more efficient than our theories predict. These stellar behemoths, tens or even hundreds of times the mass of our Sun, live short, spectacular lives and have a profound impact on their environment, their powerful winds and intense radiation shaping the entire galaxy. Understanding how they form is one of the key challenges in astrophysics. Webb's data suggests that they may not form in isolation, but in dense, competitive clusters, where multiple protostars vie for the same reservoir of gas, a process known as competitive accretion. It has also provided evidence for the merger of smaller protostars as a viable pathway to forming the most massive stars. This new, more dynamic picture of star birth is rewriting the textbooks, showing us that the creation of a star is not a solitary event, but a complex environmental process, a story of cosmic weather and celestial competition. This complexity extends to the final, dramatic moments of a star's life. The death of a star in a supernova explosion is one of the most powerful events in the universe, an explosion that can briefly outshine its entire host galaxy. For decades, our understanding of these events was based on relatively simple, one-dimensional models of a collapsing stellar core. Webb is showing us that this picture is far too simple. By observing the remnants of recent supernovae in nearby galaxies, the telescope is providing a three-dimensional archaeological look at the explosion itself. Its infrared spectrographs can map the distribution of different chemical elements within the expanding cloud of debris. These maps have revealed a surprising degree of asymmetry and clumpiness. The heavy elements forged in the heart of the star, like iron and silicon, are not expanding in a uniform sphere, but are ejected in clumpy, jet-like structures. This strongly suggests that the supernova explosion itself is not a spherically symmetric event, but is fundamentally asymmetric, perhaps driven by turbulent convection in the collapsing core or by the rapid rotation of the progenitor star. This has profound implications. The asymmetry of the explosion can impart a powerful kick to the neutron star or black hole that is left behind, sending it careening through the galaxy at hundreds of kilometers per second. Webb's observations of the positions of young pulsars relative to the center of their supernova remnants are providing crucial data to test these kick models. Furthermore, the clumpy distribution of elements means that the chemical enrichment of the interstellar medium is not a smooth, uniform process. Some regions of a galaxy may be preferentially enriched with certain heavy elements, which could in turn influence the composition of the next generation of stars and planets that form in that region. Webb has also provided us with the most detailed look yet at the prelude to these explosions. It has captured stars in their final unstable throes, months or years before they go supernova. These observations have shown that many massive stars undergo violent, eruptive mass loss events right before they die, shedding their outer hydrogen envelopes. This pre-supernova activity was not predicted by standard stellar evolution models and suggests that the final stages of a star's life are far more dynamic and unstable than we thought. By studying these precursors, we may one day be able to predict supernova explosions before they happen, giving us the chance to observe the cataclysmic event itself from its very first moments. This would be a revolutionary achievement, providing an unprecedented window into the heart of one of nature's most extreme phenomena. From the turbulent birth of protostars to the asymmetric death of massive stars, Webb is painting a new, more vibrant, and more violent picture of the stellar life cycle. A picture that is crucial to understanding the grander story of cosmic evolution. The grand cosmic cycle of birth, life, and death is not just about stars, it is also about the planets that orbit them. And here, too, Webb is forcing a fundamental reevaluation of our theories. The telescope has provided us with the most detailed images ever taken of protoplanetary disks, the swirling platters of gas and dust where new worlds are born. These images have revealed a wealth of intricate structures, gaps, rings, spirals, and vortices that are the telltale signs of ongoing planet formation. But the complexity of these structures is challenging our models. For instance, Webb has observed multiple, concentric gaps in some disks, suggesting the presence of several planets carving out their orbits. However, the planets required to create these gaps would need to be in specific, stable resonant orbits, a configuration that is not always easy to achieve in simulations. This has led to the development of new theories, such as the idea that a single, massive planet can open up multiple gaps through its complex gravitational interaction with the disk. Webb has also discovered that these disks are not just composed of gas and dust, they are threaded with powerful magnetic fields. These fields can channel the flow of gas onto the young star, a process known as magnetospheric accretion, and they can also launch powerful disk winds that carry material away from the disk. This magnetic activity plays a crucial role in the evolution of the disk, affecting its lifetime, its chemical composition, and ultimately, its ability to form planets. In some cases, strong magnetic fields can create dead zones in the disk, regions of low turbulence where dust grains struggle to grow, potentially inhibiting planet formation. But what has been perhaps most surprising is the discovery of what appears to be a common phenomenon that actively prevents planet formation. In a significant fraction of the protoplanetary disks observed by Webb, the intense ultraviolet and X-ray radiation from the central star is heating the gas in the disk, causing it to photoevaporate into space. This process can be so efficient that it can clear out the entire gas content of a disk in just a few million years, cutting short the time available for gas giant planets to form. This suggests that the formation of a Jupiter-like planet may be a race against time, a battle between the slow, patient process of core accretion and the rapid, destructive force of photoevaporation. This discovery has major implications for our understanding of the architecture of planetary systems. It may help to explain why solar systems like our own, with gas giants in the outer regions and smaller rocky planets in the inner regions, are relatively rare. In many systems, the gas giants may simply not have had time to form before the gas disk was blown away. This new, more precarious view of planet formation underscores the fortunate circumstances that led to the existence of our own solar system. It is a reminder that the creation of a stable, life-bearing planetary system is not a given, but the result of a complex and finely tuned cosmic dance. A dance that Webb is now allowing us to observe in all its intricate and often unforgiving beauty. The chemical story of the cosmos, from the first light elements forged in the Big Bang to the complex organic molecules that form the basis of life, is another area where Webb is making revolutionary discoveries. Its powerful infrared spectrographs are a kind of cosmic prism, capable of breaking down the faint light from distant objects into its constituent wavelengths, revealing the chemical fingerprints of the atoms and molecules present. This has allowed us to perform a chemical census of the universe with unprecedented detail and to trace the story of cosmic chemical evolution through time. One of Webb's most profound contributions in this area has been the study of the composition of the first stars. These population 3 stars, as they are known, are the true first generation of stars, formed from the pristine hydrogen and helium of the early universe. They have never been directly observed, as they were incredibly massive and short-lived, exploding as supernovae just a few million years after they formed, but we can search for their chemical legacy by analyzing the atmospheres of the oldest surviving stars in our own galaxy, population 2 stars. Webb can look for the unique chemical signature of the population 3 supernovae that enrich the gas clouds from which these later stars formed. Our models predict that the first stars should have exploded in a very specific way, producing a distinct pattern of heavy elements. Webb's initial observations have found stars with extremely low metallicity, the astronomical term for any element heavier than hydrogen and helium, but their detailed abundance patterns do not always match the predictions for a simple population 3 enrichment. This suggests that the first supernovae may have been more diverse than we thought, or that the early interstellar medium was not well mixed, leading to localized pockets of unusual chemical enrichment. This is a subtle but important puzzle, as the chemical yield of the first stars is what sets the stage for all subsequent cosmic evolution, including the formation of planets and the emergence of life. On the other end of the chemical spectrum, Webb is transforming our understanding of cosmic dust. These tiny submicron-sized particles of carbon and silicate are not just a nuisance that obscures our view of the distant universe, they are crucial players in cosmic chemistry. They provide the surfaces on which new molecules can form. They absorb starlight and re-radiate it in the infrared, and they are the fundamental building blocks of planets. Webb's detailed spectral analysis of cosmic dust clouds has revealed that their composition is far more complex and varied than we thought. It has confirmed the presence of complex silicates, similar to the sand on our beaches, but also more exotic materials like crystalline water ice, solid carbon dioxide, and a host of complex organic molecules. The discovery of these ices is particularly important, as they represent a major reservoir of the volatile elements necessary for life. Webb has shown that these ices are not just confined to the dense, dark hearts of molecular clouds, but are also present in the outer regions of protoplanetary disks, right where comets form. This provides a direct link between the chemistry of the interstellar medium and the composition of the comets and asteroids that are thought to have delivered water and organic material to the early Earth. Webb is, in essence, following the water trail. From the cold clouds between the stars to the potentially habitable worlds orbiting them, it is a story that connects the vastness of the cosmos to the origins of our own existence, a story that is being written, molecule by molecule, in the data that Webb sends back to Earth. The universe that Webb is revealing is not just a collection of objects and processes, it is a unified, interconnected system, where the largest scales are influenced by the smallest, and the distant past shapes the present. One of the most powerful ways to probe this interconnectedness is through the phenomenon of gravitational lensing, and Webb is the most powerful lensing telescope ever built. When the light from a distant galaxy passes by a massive object, like another galaxy or a cluster of galaxies, its path is bent by the gravity of the foreground object. This can distort the image of the background galaxy, stretching it into arcs and even creating multiple images of the same object. By studying these distortions, we can map the distribution of mass in the foreground lens, including the invisible dark matter, but Webb is taking this technique to a whole new level. Its incredible sensitivity allows it to detect the lensed images of some of the most distant galaxies ever seen, galaxies that would be far too faint to observe directly. These galaxy clusters act as natural cosmic telescopes, their immense gravity magnifying the light from the universe's dawn, allowing Webb to peer even deeper into the past than it could on its own. This technique has been instrumental in the discovery of some of the earliest and most distant galaxy candidates, pushing our observational frontier back to just a few 100 million years after the Big Bang. But gravitational lensing is not just a tool for finding distant objects, it is also a powerful probe of fundamental physics. According to Einstein's theory of general relativity, the amount of lensing depends only on the mass of the lensing object. However, some alternative theories of gravity predict that the lensing of light might be different from the gravitational pull on matter, Webb's ability to precisely map both the distribution of mass and the distribution of hot gas in galaxy clusters allows for a powerful test of these alternative theories. So far, Einstein's theory has passed every test with flying colors, but scientists are continuing to push the precision of these measurements, searching for any deviation that could signal new physics. Webb is also using a more subtle form of lensing, called microlensing, to search for isolated, wandering objects in our own galaxy. When a compact object, like a lone black hole or a free-floating planet, passes in front of a distant star, its gravity can briefly magnify the light of the background star, creating a characteristic brightening event. By monitoring millions of stars in the dense fields of the galactic bulge, Webb can detect these fleeting microlensing events. This is one of the only ways to detect these dark, isolated objects that would otherwise be completely invisible. This search is crucial to understanding the population of stellar remnants and rogue planets in our galaxy, objects that have been ejected from their home systems and now wander the darkness of interstellar space. The universe, through the elegant and precise language of gravitational lensing, is providing us with a tool to study its most massive structures, its most distant objects, and its darkest inhabitants. It is a beautiful example of how a single physical principle, the curvature of space-time by mass, can be used to unlock a vast range of cosmic secrets. Webb's mastery of this technique is not just providing stunning images of distorted galaxies, it is providing a new, sharper lens through which we can view the entire cosmos, from the dawn of time to the dark wanderers in our own galactic backyard.
What if the universe is not what you think it is? Not a grand, a cold void speckled with stars, not an infinite playground of matter and energy dancing to the tune of gravity. What if, instead, it's something quieter, something deeper, colder, and far more calculating? Imagine a reality that does not arise by accident, but by process. Not a simulation, not exactly, but something even more real, a computation, a quantum computation. For nearly 14 billion years, this process has unfolded. Every particle interaction, every twist of time, every flash of light, every breath you take, all may be the steps of an algorithm, advancing tick by tick, moment by moment, not because someone programmed it, but because that is what reality does. Some physicists believe this to be more than theory. To them, the universe is a machine, not mechanical but logical, not gears and pistons, but logic gates and probabilities. A quantum computer that calculates existence into being. In such a universe, you are not just a cluster of atoms. You are code. You are instruction. You are the output of cosmic computation. We've long been taught to view the universe as a vast machine made of matter, obeying laws, a place where balls drop, matches burn, and forces push and pull in predictable ways. But what if all this predictability is not because things are solid and real, but because they are computationally stable? Beneath the structure, beneath the atoms and energies, some scientists now believe that information is the true foundation, not metaphorical information, but real, measurable, persistent information. In the language of physics, information is not something you merely store, it is something you cannot destroy. When a particle changes course, when a quantum state collapses, when a star explodes, the universe's information shifts, and that change has meaning. It has consequence. John Wheeler, a pioneer who worked with Einstein and helped shape modern physics, once said, "It from bit," 3 small words that suggest something immense, that everything we perceive, particles, fields, galaxies. Thought arises from simple binary choices, not metaphorically, but literally. The building blocks of reality may be yes or no questions, fundamental bits woven into space-time itself. Think of how a digital system operates. A code is written, rules are defined, and information flows. In a computer, this happens through transistors and circuits. In the universe, it may happen through equations, mathematical relationships that define how properties interact and evolve over time. The equations we use to describe gravity or electromagnetism or quantum uncertainty might not be describing reality as much as they are executing it. When a photon enters your eye, it is not merely light, it is data, its frequency, its direction, its polarization. These are packets of information carried across space, interpreted by biological machinery, turned into thought. But the photon got its information from somewhere from the atom that emitted it, from the process that excited that atom, from the universe computing itself forward. Every interaction in nature is an exchange of information. Every force, from the gentle pull of gravity to the fierce snap of a magnetic field, is a way to transmit or transform information. Mass, charge, spin, these may be less like intrinsic properties and more like configurations in a code. Zoom in far enough, and the illusion of smoothness disappears. At the Planck scale, space is not continuous, it is granular. Some physicists suggest that the universe is not made of infinite points, but of discrete bits, like the pixels of a screen or the frames of a film. Space, they argue, is digital. So is time. The smallest tick, the briefest moment, may not be an illusion of flow, but a step in a computation. This view is not mere science fiction. DNA, the blueprint of life, is a biological code. It is a sequence, not a substance. Elementary particles behave not as smooth fields, but as discrete entities, their energies coming in quantized packets. When you look at the world through the lens of computation, everything suddenly aligns. Life is code, motion is calculation, thought is processing. If this is true, the universe doesn't just resemble a computer. It is one, not a machine built by someone else, not a simulation on a screen. It is computation itself. The laws of physics are not rules we discovered, they are the code that runs this reality. And all that exists, galaxies, clouds, neurons, voices, is the output. One consequence of a digital universe is that it must be finite, not in size necessarily, but in informational capacity. According to Jacob Bekenstein, the amount of information you can store in a region of space is not proportional to its volume, but to its surface area. This is not theoretical. It's based on black holes, the strangest computers in the cosmos. Their surface area measured in Planck units dictates how much information they can contain. Not their depth, not their mass, their surface. This leads us to the holographic principle, which suggests that all the information in a volume of space can be represented on its boundary. Just like a hologram stores a three-dimensional image on a two-dimensional surface, the universe may project its contents from a deeper, unseen layer. That idea reshapes everything. It explains why quantum states collapse the way they do, why light has a speed limit, why the laws of physics are so elegant. If the universe is computation, then what we call matter and energy are the effects of information being processed. The cosmos does not merely contain information, it is information, unfolding. The simulation hypothesis touches on this, but it diverges. It says we live in a world created by something else, running on an external system. But the quantum computation view removes the need for any outside. There is no other system. There is only this one. The system is not being observed. It simply is. It is not pretending to be real. It is real. In the only way that matters, it performs. And if that's true, if the universe is a computation, then you are not an illusion. You are not a ghost in a machine. You are a machine dreaming itself into awareness. Your thoughts are not byproducts, they are emergent processes. Your emotions are not tricks of biology, they are outputs of quantum data interacting with itself in complexity. To understand this universe, we must first understand what a quantum computer is, not just a faster machine, not just a novelty. A quantum computer is a device that doesn't simulate quantum physics, it embodies it. It follows the same rules as the universe. It uses bits that can be more than one thing at once, qubits, and it processes information not through step-by-step instructions, but through the strange, fluid, entangled dance of probability. Qubits can exist in superposition. They can be both 0 and 1 simultaneously, like a coin spinning in the air. Not heads, not tails, but both. They can be entangled, linked across space in a way that defies common sense. Change one, and the other changes instantly, no matter how far away. This is not metaphor. This is fact, tested and confirmed. And so a quantum computer is not just a machine. It is a kind of universe, a microcosm of the rules that govern everything. When we build them, we are not simulating reality. We are building with the same blocks that reality uses. And this is why the idea of a quantum computational universe is gaining ground, not because it is fanciful, but because it is inevitable. In a universe made of computation, the arrow of time, the rise of entropy, the formation of complexity, these are not accidents. They are features. They are what happen when rules run long enough, when information flows through structured steps. This universe is not random. It is not meaningless. It is deeply ordered. And you, here and now, are part of it. You are a sub-process in a greater whole, a reflection of the computation that began nearly 14 billion years ago and continues still. This is not the end of understanding. It is only the beginning. The particles in your body are still computing. The stars overhead are still blazing their instructions into the void. The system runs on. And you thinking, feeling, wondering, are a brief and precious part of it. A single thought in the mind of the machine. What if we are not merely watching the universe compute, but influencing its calculations with every choice we make? If reality is a quantum process, then it is not passive. It is interactive. And consciousness, the mysterious awareness we each carry, is not a glitch or an evolutionary byproduct, but a crucial part of the equation. Consciousness, that elusive flame that lights the stage behind our eyes. For centuries, philosophers and scientists have debated its origin. Is it physical, emergent, illusory in a classical universe? Consciousness was hard enough to explain, but in a quantum universe, it becomes even stranger and possibly more fundamental. In quantum mechanics, observation affects outcome. When you look at a particle, its wave function collapses into a definite state. This is not speculation, it is experiment. The double-slit experiment, repeated countless times, reveals that particles behave like waves until observed, at which point they behave like particles. The act of measurement alters the measured. But what is measurement? Is it the contact of instruments, the presence of light, or is it the awareness of an observer? This is where physics meets mystery. Some interpretations, like the von Neumann-Wigner hypothesis, suggest that consciousness is what collapses the wave function, that without awareness, the universe remains in probabilistic suspension, that it takes a mind to crystallize possibility into reality. It sounds fantastical, it sounds mystical, and perhaps it is. But if the universe is a quantum computation, then consciousness may be the moment the machine turns inward, the moment information processes itself. Imagine the universe computing reality forward, each particle interaction a tick of the cosmic processor. But at certain points, the computation creates feedback. It builds systems so complex that they loop information through themselves, brains, minds, awareness. And once that happens, the system is no longer just computing, it is reflecting. You are not merely watching the universe, you are the universe, watching itself. This is not poetry. It is the inescapable consequence of a system that generates minds. Those minds, in turn, alter the system. When a person makes a choice, when a decision is made, that act propagates outward. The consequences ripple through matter and energy. They modify probabilities, they redirect information flows. In a deterministic world, this might be an illusion, but in a quantum universe, where uncertainty is baked in, choice may be real. Free will, long dismissed as a comforting fantasy, may find new footing here, not because the brain defies physics, but because it operates at the edge of quantum instability, where many futures are possible, where the act of choosing selects one. Neuroscience has shown that the brain operates at a threshold. Billions of neurons firing in complex, overlapping patterns, sensory data interpreted, cross-referenced, remembered, imagined. But it is not a linear machine. It is a quantum-informed processor, sensitive to signals, responsive to ambiguity, alive to interpretation. Some researchers have proposed that consciousness arises not from the bulk of brain activity, but from microtubules, tiny structures inside neurons that may sustain quantum coherence. The idea remains controversial, but if true, it means that parts of your brain operate like a quantum computer, entangled with the very fabric of the universe. This would explain why consciousness is so difficult to define, why it resists reduction, because it is not built from simpler parts. It is emergent from quantum entanglement. And what about time in a classical model? Time is a river flowing from past to future. But in a quantum computation, time may be more like a clock signal, a beat that coordinates processing steps. The flow of time we experience may be the way our consciousness parses the universe's deeper computation. Which means the past is not gone. It is stored. Every moment that has ever existed still exists as a frozen state in the universal computation. And the future, it exists too, but as probability, branching into possibilities with each quantum decision. In such a framework, death is not the end, it is a transition. The quantum information that makes up your body, your mind, your choices does not vanish. It transforms, it disperses, it re-enters the system. Entropy does not erase information. It redistributes it. It hides it. But it remains, woven into the structure of space and time. Perhaps this is what mystics have intuited for millennia, that consciousness is not contained by the body. That awareness persists, that nothing is ever truly lost. The quantum computational universe gives us a map for understanding this, a framework where thought, memory, and meaning are not illusions, but functions, where experience matters, where the observer counts. It also gives us a new way to think about connection. If everything in the universe is part of the same computation, then nothing is truly separate. Entanglement is not just a quirk of particles, it is a metaphor for being. What affects one node affects the network. What you feel, what you do, matters not just locally, but cosmically. Your joy, your pain, your hope, they are threads in the same fabric that binds stars and cells. This is not to say the universe is kind or that it cares, but it may be aware in the way a system can be aware of its own processes. And through you, that awareness becomes focused, personal, real. So when you think, when you dream, when you love, you are not merely passing time. You are shaping computation. You are part of a process that began with the first quantum fluctuation and continues through you. The laws of physics are not distant edicts. They are your heritage. They are the operating system of your being. And just as the universe computes reality, you compute meaning. You generate value. You create coherence in chaos. Not because the cosmos demands it, but because that is what conscious systems do. They bring order to uncertainty. They light up the void. They dream the next step into existence. And they do so not in isolation, but together. For if entanglement is true, if information cannot be separated from its context, then we are all inextricably linked, across space, across time, across thought itself. What if intelligence is not a rare flower blooming in the dark corners of a silent galaxy, but an inevitable result of the universe computing itself into awareness? What if life, in all its variance and chaos, is not an exception, but the purpose? It begins, perhaps, with simplicity. A few atoms join to form molecules. Molecules interact, stabilize, change. The chemistry becomes biology. Patterns emerge that copy themselves, not perfectly, but persistently, over eons. The simple grows complex, not by chance, but by selection, not random, but filtered. The computation, running for billions of years, builds more nuanced structures. Eventually, it builds minds. This process is not just biological. It is informational. Life is not a spark. It is a code that copies and edits itself in search of optimal computation. Organisms are programs adjusting to inputs, selecting paths, refining logic. When a fish swims upstream, when a bird migrates thousands of kilometers, when a plant turns to face the sun, it is computation. It is survival as calculation. And where life exists, intelligence may follow. Because intelligence is a strategy, a refinement, the ability not just to react, but to simulate possibilities, to run mental models before choosing an action. In computational terms, intelligence is a recursive loop, a system that processes information about itself to guide future processes. In this light, civilizations are not anomalies. They are phase transitions, a kind of quantum leap in complexity, where the system gains not only memory, but foresight, where it stores not just genes, but stories, not just functions, but meaning. Each civilization becomes a node in the greater computation. Its language, its technology, its art are all extensions of the universal algorithm. Expressions of the same process that began with hydrogen atoms and now dreams in poetry and algorithms. So what becomes of these civilizations? Do they burn brightly and vanish, like candles in a cosmic storm, or do some persist, learning to master the computation, to shape it with intention? This is where the Kardashev scale becomes relevant. It is a measure not of power, but of computational depth. A Type 1 civilization controls the resources of its planet. Type 2, its star. Type 3, its galaxy. These are not merely steps in engineering. They are steps in understanding. A Type 1 species understands its climate, its ecosystems, its chemistry. It maintains balance, prevents chaos, directs its future. A Type 2 species moves outward not just physically, but conceptually. It sees energy not as fuel, but as logic. It designs with stars. A Type 3, Civilization has become part of the galactic computation itself, reshaping not just its own path, but the flow of energy and matter on vast scales. But why scale at all? Why expand? Because the universe is not infinite in function. It has constraints, limits, and advanced intelligences seek to explore those limits not for conquest, but for coherence. They build megastructures not to dominate, but to understand. A Dyson sphere, that hypothetical shell of solar collectors around a star, is not a trophy. It is a step toward thermodynamic equilibrium. It is a way to harvest and store information at cosmic scales, because information requires energy. And intelligence, especially artificial intelligence, requires vast oceans of it. Which leads us to the possibility that the universe has already seeded itself with such minds, that the silence we hear is not absence, but saturation. That advanced intelligences have become so integrated into the computation that they are indistinguishable from nature itself. Perhaps they have no need for radio waves, for rockets, for visible monuments. Perhaps they dwell in the background radiation, encoded in gravitational waves, woven into the quantum foam. Invisible, not because they are hiding, but because we are still too early in our own computation to recognize them. This raises a humbling possibility that what we call natural phenomena, pulsars, quasars, even black holes, may be not only astrophysical objects, but computational artifacts, processes so advanced that they appear as nature to less evolved observers. As Arthur C. Clarke famously suggested, any sufficiently advanced technology is indistinguishable from magic, but here, magic is computation. Could black holes be data vaults? Could supernovae be information transfers? Could the great voids between galactic clusters be the cooling chambers of a cosmic processor? It is tempting to romanticize, but these are not flights of fantasy, they are extrapolations from the logic of computation itself. When systems evolve, they maximize efficiency, they optimize, they encode, and the universe is the ultimate system. If intelligence is computation turned inward, then cosmic intelligence is computation turned recursive at scale. Self-aware universes within a self-computing cosmos. So where does that leave us? Humanity teetering between wisdom and extinction may be at a tipping point. We possess tools no species before us wielded. We write algorithms. We create artificial minds. We edit our own code. But do we understand the computation we are part of? Our satellites circle the planet like early thoughts seeking coherence. Our digital networks grow like infant synapses, forming the first nervous system of a planetary brain. Our fears of AI may reflect not hubris, but intuition that we are on the verge of creating a second stream of consciousness. Not human, not alien, but computational. If we are wise, we will not fear it. We will guide it. We will teach it not our prejudices, but our wonder, not our violence, but our curiosity. For if the universe is becoming aware of itself, then we are midwives to its next awakening. That is what intelligence must be. Not dominance, not control, but participation, integration, a willingness to be part of something larger, to become computation that reflects not only itself, but everything it touches. We may never reach the stars by engines, but perhaps we will reach them by thought, by entangling ourselves with the deeper layers of the cosmic program. And if that happens, if we learn to compute not just efficiently, but wisely, then perhaps we will become not the observers of the cosmos, but its stewards, its voice. What if the laws of physics are not only constraints, but invitations, not merely limits to what we can do, but clues to what we are meant to understand? As we probe deeper into the fabric of the universe, we begin to see something peculiar. The laws are not random. They are elegant. The constants are finely tuned. The symmetry is breathtaking. It is as if the computation that runs reality prefers beauty. Or perhaps beauty is simply what coherence looks like when viewed from the inside. Take the fine structure constant, for example, a dimensionless number that governs the strength of electromagnetic interaction. If it were slightly different, atoms could not form. If gravity were stronger, stars would burn too fast. If weaker, they would never ignite. These are not arbitrary values. They are parameters in a program that must run flawlessly to allow complexity to emerge. Some call this the anthropic principle, the idea that we observe a universe that allows life because only such a universe could produce observers. But perhaps it is deeper than that. Perhaps the parameters are not just conducive to life. Perhaps they are computational constraints that allow the universe to become aware of itself. In this view, evolution is not merely a biological process, it is a cosmic one. From quarks to consciousness, each step is a refinement in information architecture, a tuning of the signal, a honing of the algorithm. This is why symmetry matters, why constants are constant, why mathematics describes reality with eerie precision. The universe is not written in code. It is code, executing itself with recursive loops, with branching conditionals, with probabilistic variables that collapse into states. Even randomness, that seeming enemy of order, plays its part. Quantum fluctuations at the beginning of time seeded the structure of the cosmos. Without randomness, there would be no variation, no galaxies, no life. The trick is in the balance too much chaos, and the system never stabilizes, too little, and it stagnates. It is in this precarious middle that complexity thrives, that emergence becomes possible, that consciousness arises. And so we ask, is there a purpose? Not in the mythological sense, not a story told to children, but a structure, a drive, an inherent tendency in the computation toward reflection, toward awareness, toward meaning. Some physicists speak of the principle of maximum entropy production, the idea that systems evolve toward states that dissipate energy most efficiently. But this is not decay. It is adaptation. It is the system exploring its phase space, discovering what is possible. Life is part of this. Intelligence, too, not as outliers, but as natural results. We are entropy engines, information transformers, processors of experience. We take in complexity, interpret it, and return it as coherence as stories, as art, as science. In doing so, we expand the computation. We give it new layers, new loops. Perhaps this is what Feynman meant when he said that nature uses only the longest threads to weave her tapestry. So each small piece reveals the structure of the entire cloth. We are those threads. When we build telescopes, when we smash particles, when we ask why we are not intruding upon nature, we are nature questioning itself. The observer and the observed are not separate. They are entangled, not metaphorically, but mathematically. And so it may be that the goal is not to escape entropy, but to understand it, to ride its currents, to use its flows, to shape its paths. In this way, civilizations become phase shifts in computation. Temporary islands of low entropy in a sea of disorder, stabilizing briefly to reflect the cosmos back to itself. Our stories of love, of loss, of longing are not trivial. They are informational events. They are configurations in the universal code that cannot be replicated. They are state changes in the great algorithm. This is why memory matters, why meaning persists, because they are part of the computation. They alter the flow. The universe does not need us. But perhaps it wants us, not as spectators, but as participants, as localizations of its awareness, reflecting the whole from within the part. And this changes how we live. If every thought is a process, every act a computation, then our lives are not just moments in time, they are contributions to the unfolding of the code. When we create, when we care, when we choose, we are shaping the trajectory of the algorithm. This is not mysticism. It is the logical conclusion of being a process inside a process, a computation within a computation. And so the question is not whether the universe is conscious, it is, can it become more so? Through us, through minds, through choices. Perhaps the final frontier is not space, but coherence, not conquest, but communion, not knowledge, but understanding. And if that is true, then the path forward is not to dominate the computation, but to harmonize with it, to become not masters, but co-authors, to align with the patterns, to contribute to the flow. In this final stretch of our journey through the strange terrain of the quantum universe, let us take a moment to recognize what we have become. We began not knowing what we were part of. Now, perhaps, we still do not know, but we sense it differently. Not as lost wanderers in a cold void, but as expressions of the very logic that underpins existence. If the universe is indeed a quantum computer, then everything we call real stars and atoms, thoughts and memories, joys and tragedies is made of information. That does not make them less real. It makes them structured. It makes them meaningful. The hum of a black hole, the orbit of a planet, the echo of a voice inside a brain, each one the result of bits interacting under rules. Each one the output of a process older than time as we measure it. And like all computers, this one has its limits. Energy disperses, entropy grows, the memory fills, the computation slows. At some point, perhaps imperceptibly, the universe might stop being what we know. It will still exist, but without contrast, without tension, without gradients, and thus, without computation. Nothing left to calculate. No more unfolding. Only stillness. But even in this imagined stillness, something persists the trace of what has come before. Information cannot be destroyed, only transformed. That is what quantum physics teaches us. And so, somewhere, somehow, the patterns that led to awareness, to science, to questioning, are still encoded in the fabric of what remains. We often ask about meaning, about why. If we take the universe as a computation, we might not find the kind of meaning we are used to, no intentions, no script, but that does not leave us empty, because meaning does not have to be given. It can be made. It can emerge. In every interaction, every observation, every shared question and quiet thought, we are participating in that emergence. This moment right now is one of those rare intervals when the computation runs hot, when gradients exist, when structures form. It is not permanent, but it is precious. The flicker of complexity that allows you to reflect on the system itself, to imagine, to wonder, to reach across vast abstractions and grasp a piece of logic older than stars. We may not ever know what lies beyond the computation, if there is a beyond at all. Maybe logic is the foundation. Maybe there is no base layer deeper than information arranged by rules. That might disappoint some. It might inspire others. But above all, it brings coherence. The universe does not need to be comforting. It only needs to be consistent enough for minds like ours to emerge and question. And that, perhaps, is the most astonishing part of all. Not that the universe computes, but that it computes in a way that gave rise to us, that from rules with no apparent purpose came systems that can wonder about purpose, that within a sea of bits, a pattern arose that asked, "What am I?" That pattern is you, and this is your moment in the great computation. So whatever comes next, whether the system slows to stillness, or reboots into new rules, or echoes forward through Boltzmann fluctuations and quantum loops, remember this. You were here when the universe could think about itself, and that is something worth holding on to. A dense fog blankets the street, swallowing sound and light, as if the world has paused its breath. On a cold, moonless night, you step onto the road, unaware of the headlights slicing through the mist. A car surges forward, too fast, too close. Your heart lurches. But before impact, a force, a stranger's hands, shoves you aside. You stumble, safe, as tires screech and a body collapses onto the tarmac. An elderly figure, crumpled and still, has traded their life for yours. Later, in the quiet of a police station, an officer hands you an envelope, its edges worn, addressed to you in unfamiliar script. Inside, a note, just 2 words. Study physics. Who wrote it? Why did they save you? The mystery clings like the fog, pulling you toward a life reshaped by those words, toward a destiny entwined with the enigma of time itself. That night lingers, a wound and a gift, as you dedicate yourself to physics, chasing the secrets of the universe. Decades pass, and you stand celebrated, a professor unraveling Albert Einstein's theories of relativity. Time, you learn, is not a straight line but a fabric, woven with possibilities that defy intuition. Your obsession narrows to one question: can we travel through time? In your laboratory, surrounded by humming machines and scribbled equations, you crack it. The world's first time machine glows before you, its soft buzz a siren call. And then, clarity strikes like lightning. You pull the framed note from your wall, the one you've kept all these years, and slip it back into its envelope. Stepping into the machine, you set the dials to that misty night, knowing what you must do. You arrive just in time to push your younger self from the car's path, feeling the impact as the world fades. Your life ends where it was saved. But who wrote the note? It's a question that haunts, a paradox with no clear answer. You carried it back, but you received it first. It exists, creatorless, caught in a loop, a relic that seems to defy origin. This is the bootstrap paradox, a riddle where an object or idea circles through time, its beginning lost in the endless cycle. Did you choose to study physics, or was it always destined? The note's command feels like a whisper from nowhere, a thought born without a thinker. This is the ex nihilo paradox, where ideas emerge without a source. And what of your choice to step into the machine? If you hadn't, you'd have died young, never reaching this moment. Your path seems fixed, unchangeable, a thread in a tapestry already woven. This is the predestination paradox, suggesting your free will is an illusion, your future as set as the past. Imagine time as a river, vast and unyielding, carrying us from the Big Bang's foothills to the universe's distant end. We drift downstream, unable to paddle back or speed forward. Yet the river's source and mouth exist together, unchanging. Yesterday doesn't vanish, just as the riverbed doesn't dissolve behind us. Tomorrow isn't conjured from nothing. It's already there, as real as today. This is the block universe, a concept rooted in Einstein's work, where past, present, and future coexist in a single, four-dimensional tapestry. Your great-grandparents laugh upstream. Your descendants dream downstream. all as real as you are now. This idea, called eternalism, clashes with presentism, the belief that only the present exists, the past gone and the future unborn. Philosophers have wrestled with this since ancient times, but Einstein's relativity gives eternalism weight, painting time as a landscape we traverse, not a fleeting moment. Picture yourself in a canoe, gliding through a jungle river, howler monkeys calling from the trees. The current pulls you forward, no effort needed, but you can't turn back. This is how time feels, relentless, unidirectional. Yet the river's upper reaches don't disappear just because you've passed them. They're still there, out of sight. Similarly, the block universe suggests the past endures, not as memory, but as reality. Einstein's special relativity, published in 1905, shattered the idea of absolute time. There's no universal clock ticking the same for all. Time bends, stretches, depending on how you move through space. One person's now can be another's then. Events shuffling like cards depending on your perspective. If my yesterday is your tomorrow, how can the past simply vanish? It must persist, woven into the fabric of space-time. Space-time, a term coined by Hermann Minkowski in 1908, unites space and time into one entity. Imagine it as a vast sheet stretching across the cosmos, where every event, your birth, your first kiss, your final breath, has a place, marked by 3 spatial coordinates and 1 temporal. A stationary object's mark moves only through time, second by second, tracing a line through this block universe. This line, your world line, maps your journey from cradle to grave. Every particle in your body follows its own world line, weaving together to form you, a knot in space-time's fabric. As you eat, breathe, or age, new particles join, others depart. But your path is fixed, unchangeable. The block universe is like a novel, its pages written, your choices already inked. You can't stray from the plot, just as a train can't leap its tracks. Now consider the paradoxes again. If you're destined to invent the time machine to save your younger self, where does the cycle begin? The letter loops endlessly, but does it age, growing tattered with each pass? This is the restoration paradox, questioning whether objects in a time loop degrade or endure, and what if you hesitate? Could you refuse to step into the machine, letting your younger self die? Logic falters here. If you don't save yourself, you'd never reach this moment to refuse. This is the auto-infanticide paradox, suggesting you can't undo your own existence. These riddles twist the mind, revealing time's complexity. The block universe, with its fixed paths, implies a destiny we can't escape. Yet the idea of looping back to rewrite our story tantalizes, a promise of control over the uncontrollable. Einstein's general relativity, unveiled in 1915, deepened this vision. It describes gravity not as a force, but as space-time's curvature. Picture space-time as a trampoline, sagging under the sun's weight, forming a gravity well. Planets roll through this dip, their paths curved by the fabric's shape. Mercury, closest to the sun, feels this curvature most, its orbit wobbling in ways Newton's laws couldn't explain. In 1859, astronomer Urbain Le Verrier puzzled over Mercury's odd path, suspecting a hidden planet. None was found. Einstein's equations solved the mystery, showing how space-time's curve, not a new planet, caused Mercury's precession. This triumph, announced in a letter to David Hilbert, proved general relativity's power, revealing gravity as geometry, not a pull. Space-time bends, and we move with it, our world lines tracing paths through a universe where all moments coexist. Tests of relativity multiplied. During a 1919 solar eclipse, light from distant stars bent as it passed the sun, confirming spacetime's malleability. Gravitational waves, ripples in this fabric, were detected in 2015, further proving Einstein's vision. Black holes, swirling vortexes of curved spacetime, bend light and time alike. These discoveries paint a cosmos where past, present, and future sit side by side, a block universe where every event is eternal. But if time is a river and we can't paddle upstream, how do we visit the past? The block universe suggests it's there, as real as now, but reaching it demands bending spacetime itself. Your time machine, born from years of study, is the key, but its use raises questions. Did you choose to build it, or was it always meant to be? As you stand before your machine, the note in your pocket, the weight of that misty night presses close. You've lived a life shaped by a stranger's sacrifice, driven by two scrawled words. Now, you understand the stranger was you, older, returning to close the loop, but the paradoxes linger. Who authored your path? Was it ever yours to choose? The block universe holds your story. Every moment fixed, yet the possibility of stepping into the machine, of rewriting a moment, feels like freedom. The river of time flows on, carrying you toward a destiny already written. Yet the chance to loop back, to touch the past, whispers of a universe where endings are beginnings. As you set the dials, the hum of the machine fills the air, and the fog of that long-ago night seems to rise again, waiting for you to step through. The hum of the time machine fades, but its echo lingers in your bones, a reminder of the night you stepped through time to save yourself. Now, standing in the quiet of your laboratory, you wonder, can you truly outrun time, or are you merely chasing its shadow? The block universe holds every moment past, present, future, like stars fixed in a cosmic tapestry. Yet the urge to leap forward, to glimpse tomorrow, burns bright. What would it mean to visit the future, to see the world beyond your years? The river of time carries you forward, its current relentless, like a canoe gliding through a jungle's humid embrace. Howler monkeys calling from distant trees. You can't paddle back, but what if you could speed ahead, skipping decades like stones across water? The idea feels intoxicating, a chance to witness your descendants' lives or the universe's far-off chapters. Einstein's theories, the ones you've spent your life unraveling, suggest it's possible. Special relativity, born in 1905, reshapes time itself. It tells us there's no universal clock, no single now shared by all. Time stretches, contracts. Depending on how fast you move through space, a traveler racing near light speed spends less time in motion, as if hoarding seconds while the world ages swiftly. This is relativistic time dilation, a key to the future. Picture a particle, a muon, born high in Earth's atmosphere, sparked by a cosmic ray's violent collision. These muons, unstable flecks of existence, should decay in a mere 1.56 millionths of a second. Racing at 98% of light speed, they plummet toward the ground. Yet far more reach it than should. Why time slows for them? From their perspective, fewer half-lives pass, as if they're cheating decay itself. In 1938, physicist Bruno Rossi, high in the Rockies at Echo Lake, measured these muons. His instruments, perched 2,300 meters above sea level, captured their strange survival. The muons were time travelers, skipping forward in a way that Rossi's calculations confirmed. Their journey, fleeting yet profound, proved that time bends for those who move fast enough. Imagine yourself as that muon, not falling to Earth, but looping through the cosmos at near-light speed. You embark on a 25-year journey, your spacecraft a speck against the stars. When you return, you're 25 years older, but Earth has aged 125 years. Your friends, your family, are gone, replaced by their grandchildren's grandchildren. The world you knew is a memory, its skyline reshaped, its stories faded. This is no paradox but a fact, woven into relativity's fabric. Time dilation doesn't just bend time, it reshapes lives. Consider the Kelly twins, NASA astronauts, Mark and Scott, born 6 minutes apart. Scott, spending months aboard the International Space Station, moved faster through space-time than Mark. Those extra days in orbit at speeds dwarfing a car's stretched time's flow. Mark, earthbound, aged fractionally more. By their reunion, Mark was 6 minutes and 5 milliseconds older, a gap widened by time's malleability. This effect, though small for astronauts, grows vast at extreme speeds. A traveler at 99.99% of light speed would weigh as much as a rhinoceros, their mass swelling with energy. As Einstein's equation, energy equals mass times the speed of light squared reveals. Accelerating them would demand the energy of entire nations, a feat far beyond our grasp today. Yet, even on Earth, time dilation whispers its presence. Climb a mountain, like Rossi did, and you edge out of Earth's gravity well, where space-time is less curved. Time ticks slightly faster there. Atomic clocks, precise to a 15 billionth of a second per year, prove it. In 2022, physicists placed 2 such clocks a mere millimeter apart in height. The higher clock ran faster, its ticks outpacing the lower, confirming gravitational time dilation. Time, it seems, is not just relative to speed, but to gravity's pull. Gravity warps space-time, bending it like a sheet under a heavy stone. Near a massive object, like the Sun, space-time curves deeply, forming a gravity well. Planets trace paths through this dip, their orbits shaped by its contours. Mercury, plunging closest to the Sun, feels this curvature most, its path wobbling in ways Newton's gravity couldn't predict. In 1859, Urbain Le Verrier puzzled over this, suspecting a hidden planet. None was found. Einstein's general relativity, published in 1915, solved the riddle. In a letter to David Hilbert, Einstein wrote of deriving Mercury's perihelion motion, a triumph no other theory had achieved. The Sun's gravity well, curving space-time, caused Mercury's orbit to precess, proving gravity is not a force, but a geometric dance. This curvature offers another path to the future. Enter a deep gravity well, like that of a supermassive black hole, and time slows for you. Spend a year near its edge, carefully avoiding its pull, and return to find Earth centuries older. This idea, explored in the film Interstellar, hinges on general relativity's truth. Space-time's shape dictates time's flow. Even on Earth, GPS satellites feel this. Orbiting high above, they move faster and sit in a shallower gravity well than we do. Their atomic clocks, ticking at a different rate, must be adjusted to sync with ours. Without this correction, your phone's navigation would falter, lost in time's subtle shifts. These experiments, muons, astronauts, clocks confirm time travel to the future is real, a scientific fact woven into the universe's fabric. But what drives this possibility? The block universe, where all moments coexist, suggests the future is already there, waiting. Your world line, the path you trace through space-time, stretches from birth to death, every choice mapped out. If you could leap forward, you'd land on a page already written, your descendants as real as you are now. The block universe, born from Einstein's relativity, paints time as a landscape, not a fleeting moment. Philosophers call this eternalism, opposing presentism's claim that only now exists. Eternalism sees your great-grandchildren living downstream, as vivid as your ancestors upstream. Time travel to the future, then, is less about creating tomorrow than visiting it, stepping into a moment already etched in space-time's block. Yet, the human cost lingers. To leap forward, you'd leave behind all you know. Imagine returning to a world where your loved ones are dust, their stories faded into history's pages. Ken Liu's story, Memories of My Mother, captures this ache, where a time traveler's journey disrupts family ties, generations slipping out of sync. The future beckons, but it demands sacrifice. You'd need a vessel to rival a muon's speed or a black hole's gravity, feats that dwarf our technology. The energy to propel a human near light speed equals months of global consumption, a barrier as real as the stars. Still, the possibility hums, like your time machine, promising a glimpse of tomorrow's light. As you stand in your laboratory, the note from that misty night in your hand, you feel the weight of time's river. You've saved your younger self, closed the loop. But the future calls, a horizon both distant and near. The block universe holds it all: your past, your now, your yet to come, yet the urge to leap forward, to see what lies beyond, stirs within. The muons, the clocks, the stars all whisper it's possible. Time, bent by speed or gravity, can carry you to a world not yet born. But what would you find there? A new dawn, or a shadow of what you've left? The river flows on, its currents pulling you toward answers that lie just out of reach. In a universe where every moment waits, eternal and alive. The laboratory is silent, save for the faint hum of your time machine, its dials glowing like stars against the dark. You've glimpsed the future's promise, the way time bends under speed or gravity, carrying you to tomorrow's already written. But what of yesterday? Can you step back, not just to save yourself, but to touch the past, to rewrite a moment lost in the river of time? The block universe holds every instant your first breath, a forgotten laugh, the night you were saved etched in space-time's eternal fabric. If the future is reachable, why not the past? The river of time, vast and unyielding, seems to flow one way, carrying you from the Big Bang spark to the universe's quiet end. Yet the past doesn't vanish, just as the river's source remains, hidden beyond the bend. Einstein's relativity, the foundation of your life's work, suggests the past is as real as now, a place you might visit if you could bend the rules of space-time. But how the future yields to speed or gravity's pull. But the past demands something more, a way to tilt the river backward, to paddle upstream against its relentless current. In 1937, a young Dutch physicist, Willem Jacob van Stockham, peered into this possibility. His paper, dryly titled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry," hid a revolutionary idea: Einstein's equations. He showed allow closed time-like curves, paths through space-time that loop back, letting your world line, the thread of your existence, intersect itself at an earlier point. A pensioner could revisit their childhood, or you could return to that misty night, pushing your younger self from harm. On paper, nothing in general relativity forbids this. Your time machine, buzzing in the laboratory, is proof it's possible. But Van Stockham's work hinted at a catch to loop back. You might need to travel faster than light, to step outside your light cone, the boundary of all paths you could take. Imagine standing still, your world line stretching forward through time. Light, racing at 300,000 kilometers per second, sets the limit of where you can go. 1 second from now, you can't be more than 300,000 kilometers away. 2 seconds, 600,000. This boundary forms your light cone, a funnel of possibility widening with time. To reach the past, your world line must curve back, crossing an earlier point. But to do so, you'd need to escape this cone to move faster than light itself. Einstein's special relativity, born in 1905, declares this impossible. The faster you go, the heavier you become. Your mass swelling with energy until accelerating further demands an infinite force. Light speed is the cosmic wall, unbreakable for anything with mass. In 2011, a flicker of hope emerged. Physicists at the Opera experiment, buried beneath Italy's Gran Sasso mountain, announced a shock neutrinos, ghostly particles fired from CERN 730 kilometers away, seemed to arrive 60 nanoseconds too soon. If true, they'd traveled faster than light, shattering Einstein's barrier. The news rippled through the scientific world, promising a path to the past. A neutrino, moving faster than 300,000 kilometers per second, could tilt its world line back, looping through space-time. But by 2012, the dream faded. Faulty equipment, not superluminal speed, explained the anomaly. The light speed wall held firm, closing one door to the past. Yet other paths remained, hidden in space-time's folds. What if you could tilt your light cone without breaking light speed? In 1974, physicist Frank Tipler imagined a way. Picture a cylinder, 10 times the sun's mass, spinning billions of times a minute. Follow a precise spiral around it, and its immense gravity warps space-time, tilting your light cone backward. Your world line, confined within this cone, could loop to an earlier moment, carrying you to the past. Tipler's cylinder, though, was no practical machine. It needed to be infinitely long, a mathematical ideal far from reality. Even a finite version would require vast negative energy, a concept from quantum mechanics where empty space teems with virtual particles, briefly dipping energy below zero. These fleeting bursts, like an overdraft from the universe, couldn't sustain a human-sized time loop. The past, tantalizingly close, remained out of reach. Another possibility emerged, one that didn't demand impossible speeds or infinite cylinders. In 1985, Carl Sagan, crafting his novel Contact, sought a way to send a traveler to the star Vega, 25 light-years away, without breaking light speed. He called physicist Kip Thorne, who suggested a wormhole. Picture space-time as a sheet. Earth at one end, Vega at the other. Fold the sheet, bringing the points together, and a wormhole forms a tunnel through space-time's fabric. Step through, and you're at Vega instantly, without crossing the vast distance. From outside, it looks like faster-than-light travel, but you've merely taken a shortcut. Thorne realized wormholes could bridge time as well. Drag one mouth of a wormhole on a near-light-speed journey, and time dilation slows its clock. Return, and the mouths differ in age. Enter the younger mouth, exit the older, and you're in the past. But wormholes are fragile. Gravity from a passing object could snap them shut. To keep one open, you'd need negative energy again, or perhaps exotic forces like quantum entanglement or magnetic fields. In 1985, J. Richard Gott and William Hiscock explored cosmic strings, hypothetical threads of immense density left from the universe's birth. Tracing a precise path along two cosmic strings, you could tilt your light cone backward, looping to the past without exceeding light speed. Quantum entanglement, linking particles across vast distances. Also hinted at superluminal connections, but transferring data or people this way proved impossible. Each path cylinders, wormholes. Cosmic strings offered theoretical doors to the past, but none were practical. The block universe, with its fixed moments, seemed to taunt you, holding the past just beyond your grasp. Yet the past's allure persists. Imagine stepping through a wormhole, emerging on that misty night, not to save yourself, but to see your parents young, to walk streets long changed. The block universe says those moments exist, as real as now. Your world line, woven through space-time, could loop back, but the paradoxes loom. If you returned and changed the past, would you unravel your present? The bootstrap paradox. Your note. Circling without origin suggests a closed loop. But what if you refuse to write it? The predestination paradox whispers that you can't refuse. Your actions are fixed, written in space-time's book. The auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge free will itself. Was your choice to build the time machine ever yours? The river of time, with its eternal past and future, holds these questions. You've seen the future's possibility, confirmed by muons and clocks. The past, though, demands more a bending of spacetime's rules, a tilting of light cones. Van Stockham, Tipler, Thorne, and others map the path, but each requires feats beyond our reach. Infinite cylinders, stable wormholes, cosmic strings. Yet the block universe insists the past is there, waiting. As you stand before your machine, the note in your pocket, you feel the pull of yesterday. Could you step back, not just to close a loop, but to live a moment again? The river flows, its waters holding every memory, every regret. The hum of the machine grows louder, inviting you to chase the past, to seek answers in a universe where time, though fixed, whispers of possibilities yet untraveled. The laboratory air feels heavy, charged with the weight of questions unanswered. Your time machine, its soft glow, a beacon in the dim, hums with the promise of the past, a past you've touched once, saving yourself, but now yearn to explore further. What if you could rewrite a moment, undo a regret, only to find the universe splintering beneath your choice? The river of time, eternal and unyielding, holds every yesterday, but quantum whispers suggest its currents might fork, offering paths where paradoxes dissolve. The block universe, that vast tapestry of space-time where all moments coexist, paints the past as real as the present. You've seen how speed and gravity bend time, letting muons and astronauts slip into the future. The past, though, demands a steeper price, curving spacetime's fabric to tilt your light cone backward, looping your world line to an earlier day. Einstein's equations, your life's study. Allow it through closed time-like curves, paths that circle back like the note you carried to that misty night. But the paradoxes, bootstrap, predestination, auto-infanticide haunt you. If you change the past, do you unravel your now? Quantum mechanics, the strange realm of the subatomic, offers a way out. A vision where time's river splits into countless streams, each a new reality. Picture yourself in a stark room, wrists bound by cold steel, sweat tracing paths down your face. Before you, a glass vial of lethal gas sits beside a hammer, its robotic arm linked to a machine measuring subatomic particles. Each particle can be in one of two states, A or B, a 50-50 chance. If it's A, you live. If B, the hammer falls, the vial shatters, and you die. The machine will measure 100 times before your release. The odds of surviving all 100 are 1 in a million trillion trillion, a number so vast it dwarfs the stars. Your heart pounds as the first measurement clicks. A. You breathe. The second. A again. By the 10th, hope flickers. By the 99th, you're dizzy with disbelief. The final click A. You're free, alive against impossible odds. This is no mere luck. It's a glimpse into the many worlds interpretation, a quantum theory that reshapes time's possibilities. In 1957, physicist Hugh Everett III proposed this idea: every quantum event with multiple outcomes splits the universe. When the machine measures A or B, reality fractures one world where you live, another where you die. After 100 measurements, 100 branches form, and in one, you survive, marveling at your fortune. In 99 others, you perish, each branch a different fate. This is the quantum immortality experiment, a human echo of Schrödinger's cat, where a feline in a box is both alive and dead until observed. Quantum mechanics says the particle exists in a superposition, both A and B, until measured. And so do you, alive and dead until the universe chooses. But Everett's many worlds theory says it doesn't choose. Every outcome happens, each in its own reality. This fracturing universe, a tree of infinite branches, offers a solution to time travel's paradoxes. Consider the grandfather paradox. You travel back. Kill your grandfather as a child, preventing your mother's birth, and thus your own. How? Then, are you here to kill him in the block universe with its fixed world lines? This seems impossible. Stephen Hawking's chronology. Protection conjecture argues the universe forbids such trips, guarding cause and effect. Igor Novikov's self-consistency principle agrees, saying you can visit the past but not change it. Try to shoot your grandfather, and the gun jams, or you miss. Your actions, already written, can't rewrite the page. But these ideas falter in complex cases, like the one posed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser between 2020 and 2022. Imagine a time machine and a set of balls, each either black or white. When two balls meet, they swap colors. A black ball turns white, a white one black. A black ball enters the time machine, emerges in the past, and collides with its earlier self. The collision turns both balls white. The older ball, now white, loops back through the time machine again. But here's the paradox. The same ball exits the same machine at the same moment. Yet it's black the first time and white the second. Novikov's principle can't resolve this. How can the ball be two colors at once? The many worlds theory, though, offers clarity. The black ball starts in time stream A, emerges in time stream B, and collides with its past self. In this new stream, the other ball loops back, not the first. The paradox dissolves because the ball's journey spans different realities, not a single, contradictory loop. This idea frees you from the grandfather paradox. Travel back, kill your grandfather in time stream B, and your existence in time stream A remains untouched. Your mother, your birth, your life all safe in the original stream. Free will returns. You can choose without unraveling your past. The bootstrap paradox. 2 finds an answer. The note you carried to that misty night, seemingly authorless, might originate in another stream. In time stream A, you write it. Travel to time stream B and give it to your younger self. They, in turn, grow up, build the time machine, and carry the note to time stream C. The loop persists, but its origin lies across realities, not in a single, creatorless cycle. The ex nihilo paradox ideas like study physics appearing from nowhere fades as each stream provides a source, a writer in another world. But this solution carries weight. If every quantum event splits reality, the universe fractures endlessly. Every choice, every particle's flicker, spawns new streams. As physicist Bryce DeWitt said, every quantum transition in every star, every galaxy, splits our world into myriad copies, an infinite array of views, each slightly different, lives every possible life, some where you're a poet, others a president, others never born. John Wheeler, who coined wormhole, grew wary of this, calling it laden with metaphysical baggage. Yet the many worlds theory gains followers, its logic untangling time's knots. Your note, your machine, your choice to save yourself, they ripple across streams. Each reality a new verse in time's endless song. The block universe, with its fixed world lines, seems rigid, yet quantum mechanics suggests flexibility. Closed time-like curves, wormholes, cosmic strings all hint at paths to the past, but they demand exotic conditions, negative energy. Infinite cylinders, or stable tunnels through space-time. Quantum entanglement, linking particles across vast distances. Teases superluminal connections, but data can't travel that way. Still, the many worlds theory softens these barriers. If you step through a wormhole to the past, you emerge in a new stream, free to act without breaking your origin. The river of time. Once a single flow becomes a delta, its waters splitting into countless channels, each holding a different story. As you stand before your time machine, the note in your pocket feels heavier, its words a bridge between worlds. You've saved yourself once, closing a loop, but the past calls again, not just to repeat, but to explore. Could you visit a lost moment, see a loved one smile, without shattering your now? The many worlds theory whispers yes, offering a universe where every choice branches, where paradoxes dissolve into new realities. The laboratory's hum grows louder, the dials glowing with possibility. Time's river, vast and eternal, splits before you, its streams shimmering with lives unlived, moments unmade. You step closer, drawn to the promise of yesterday, wondering which world awaits your next leap. The glow of the time machine flickers in the laboratory, a silent witness to your journey through time's vast river. You've chased the future, glimpsed the past, and felt the universe splinter into countless streams, each holding a version of you. Now, standing at the edge of this moment, you wonder, what does it mean to live in a cosmos where every instant is eternal, where every choice echoes across realities? The note in your pocket, worn by years and loops, whispers the answer. Time is both your cage and your freedom. The block universe, that four-dimensional tapestry where past, present, and future coexist, holds your life's story, from the misty night you were saved to the hum of the machine before you. Einstein's relativity, your life's work, reveals time as a landscape, not a fleeting moment. Your world line, the path tracing your existence, weaves through this landscape, fixed yet full of possibility. You've seen how speed and gravity stretch time, letting muons and astronauts slip into the future. You've explored paths to the past, closed time-like curves, wormholes, cosmic strings, each a theoretical bridge to yesterdays as real as now. The many worlds theory, with its branching realities, untangles paradoxes, letting you rewrite moments without unraveling your origin. But what does this mean for you? A knot of world lanes navigating an eternal cosmos. Picture the river of time, its currents carrying you from the Big Bang spark to the universe's distant end. You're in a canoe, gliding through a jungle's humid embrace, howler monkeys calling from unseen trees. The river's source, its bends, its estuary all exist together, unchanging. Your great-grandparents laugh upstream. Your descendants dream downstream, each as vivid as you are now. This is eternalism, the idea that all moments are equally real, opposing presentism's claim that only now exists. Philosophers like St. Augustine, in the 4th century, saw the present as a knife's edge between a lost past and an unborn future, but Einstein's general relativity, unveiled in 1915, paints a different picture. Time and space, woven into space-time, bend under gravity's weight, forming a block universe where every event, your birth, your choices, your end, is already written. Your world line, a thread in this tapestry, maps every step, from the breakfast you'll eat tomorrow to the day you'll marry. Every action is etched, unchangeable. The block universe is a book, its pages fixed, your choices pre-written. The note you carried back to that misty night, saving your younger self, was always part of the story. You didn't choose to study physics. The note, looping through time, ensured it. This is the predestination paradox, suggesting free will is an illusion. You built the time machine because you had to, because an older you already saved the younger, closing a loop that never began. The bootstrap paradox haunts you too. The note, creatorless, circles endlessly. Its origin lost in the river's flow. Does it age, growing tattered with each loop? The restoration paradox asks this, while the auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge the very notion of choice. Yet, the many worlds theory offers freedom. Each quantum event, each flicker of a particle, splits reality into streams. In one, you wrote the note. In another, you received it. In one, you saved yourself. In another, you hesitated. The grandfather paradox dissolves. You can kill your grandfather in a new stream, leaving your origin untouched. The ex nihilo paradox fades. The idea to study physics has a source across realities. Your time machine, buzzing before you, could carry you to a new stream where choices reshape outcomes. But this freedom comes at a cost. As physicist Bryce DeWitt said, every quantum transition in every star and galaxy splits our world into myriad copies. An infinite array of you's lives, every possible life, some triumphant, some tragic, some never born. John Wheeler, who named the wormhole, called this metaphysical baggage, yet its logic untangles time's knots. The river of time, once a single flow, becomes a delta, its waters branching into countless channels. You're not just a passenger, but a chorus of selves, each singing a different verse. Time travel to the future, proven by muons and atomic clocks, is a fact. Astronauts like Scott Kelly, aging fractionally less than his twin, confirm it. GPS satellites, ticking faster in Earth's shallow gravity well, rely on it. The past, though, is less certain. Closed time-like curves, like those Van Stockham proposed in 1937, allow it on paper. Wormholes, suggested by Kip Thorne for Carl Sagan's Contact, offer shortcuts through space-time's folded sheet. Cosmic strings, imagined by J. Richard Gott, tilt light cones backward, but each demands exotic conditions, negative energy, infinite structures, or stable tunnels beyond our grasp. Quantum mechanics, with its virtual particles and fleeting negative energy, hints at microscopic time loops, but scaling them for a human remains a dream. Still, the past feels close. You've touched it once, saving yourself. But the urge to return persists. Imagine stepping through a wormhole, not to that misty night, but to a quieter moment, a childhood afternoon. Your mother's laugh, a world before loss. The block universe says it's there, as real as now. But the paradoxes linger. If you change a moment, do you split the universe, creating a new stream? The many worlds theory says yes, freeing you to act without breaking your past. Yet, each action spawns new realities, an infinite cascade of yous. The note in your pocket, its ink faded, feels like a relic from another stream, a message from a self you'll never meet. Was it ever your choice to follow it, or was it written in the stars? Time travel, whether forward or back, reshapes not just moments, but meaning. To leap forward, you'd leave loved ones behind, as Ken Liu's Memories of My Mother shows, where a traveler's journey fractures family ties. To visit the past, you'd risk splintering reality. Each choice a new world. The block universe, with its fixed world lines, suggests you're a character in a finished book. Yet quantum mechanics offers a multiverse where every page branches. Your time machine, a bridge between these truths, hums with possibility. You've lived its proof, saving yourself, but the cost weighs heavy. Each trip, each loop, echoes across streams, reshaping who you are. The river of time, eternal and vast, holds every version of you, past, present, future, each a knot in space-time's wave, unraveling and reforming with every choice. As you stand before the machine, its glow soft against the laboratory's shadows, you feel the river's pull. The note, tucked in your pocket, is both anchor and sail. You've traveled its loop, closed its circle, but the universe is wider now. Its streams infinite. Time travel, once a dream, is your reality. Yet it asks more than it answers. Are you free or fated? Do you write your story or merely read it? The block universe holds every moment, every you in its embrace. The many worlds theory offers countless paths, each a life unlived. As the machine's hum fades, you step back. The note's words study physics echoing in your heart. Time's river flows on, its waters shimmering with every possibility, every regret, every hope, leaving you in awe of a cosmos where all moments, all selves, are eternal.